This video is part one of network basics, where I'm going to go through just some of the fundamentals that I think that's very important to know and understand when dealing with the topic of networks. First thing to note is if someone was to ask me, well, what's a network, or what does a network mean to me? I just think of it's really just a collection of objects that are related in some way. An example of that would be my family, my social network, for example. I could think of a traffic network that links cities together, for example. Okay, so just thinking of examples of networks, I think is a very good way to start. Okay, let's go through some quick terminology. Okay, so when in the topic of networks in mathematics, though, I think there's quite a bit of terminology that you need to know, and I think that's probably one of the reasons why students, I guess, initially do find this topic a little bit daunting. But in reality, we live and breathe networks on an hourly basis. It's part of our life, in fact. Just the way we interact with others and how we view our relationship with others is in itself a network. So I think, just appreciating that fact alone, I think will really drive home the point that this topic is a very important one, and it's great to articulate these kind of real life situations and really sort of study them in more detail. So let's look at this diagram. These dots, we call these dots vertices. Okay, so I'm just going to write. Okay, so these are vertices or vertex, for example, if it's singular. Okay, so there's a collection of vertices here, and we usually label them. It's not the only way, but we usually label them with a capital letter. Sometimes it could be lowercase, but so we have vertex A, vertex B, C, D, and E. Now, these represent the objects. So they could be towns, for example. They could be people. They could be, for example, transmission stations for power, or they could be pumping stations for water. I mean, it could be anything. So these lines that join the vertices, these are called edges. Okay. Again, there are other names, that we can call them, but we're just going to focus on probably the more common terminology. Okay, so vertices are linked with edges. Okay, notice here a vertex D. It seems to be like a road that leads back to itself. So it's almost like this could be town D, and sort of traveling along this edge, and you sort of come back to where you started. This is called a loop. Okay. Now, notice also from vertex A to vertex C, and vice versa, it's actually two-directional or bi-directional. So there's no direction indicated here. Notice that there's two ways to go from A to C directly. So we've got this path here, and we've also got this path here, or this edge here. These two edges, well, they could be two different roads, but linking the same two towns. These are what we call multiple edges. Okay, that term's a very important one. Okay, so because later on in the topic there's a requirement that we cannot have multiple edges between any two vertices. So I think it's good to know that whenever you see this situation, it's good to sort of put your finger on it and say, that's a multiple edge. Okay, next thing we're going to talk about is the degree of a vertex. Okay, so let's have a look at, say, for example, vertex C. So I'll use a different color here. Vertex C, the degree of a vertex talks about how many connections basically lead to it. So if you take vertex C, we have 1, 2, 3, 4. Okay, 4 connections, so leading in and out of it. So this one is degree 4. Okay, vertex E, what would be the degree of vertex E? So again, how many lines or edges are leading to E, okay, or away from E? This one is degree 1. Okay, and so on. A is degree 3, okay, B is degree 3, and D would also be degree 3, because if you were to basically ignore the loop for a moment and just look at if I was to draw a circle around D, this is a good way to I guess, to count the degree, or to determine the degree of a vertex. If you were to draw a circle around the vertex, how many edges are cut? 1, 2, 3 edges. So this this vertex D, this would be degree 3. Okay, and B is also degree 3. Okay, A is also degree 3. So quite a few degree 3s there. Okay. Now a very interesting observation here. Count the total degrees, or the total the sum of all the degrees. So 1 plus 4 is 5. 5 plus 3 is 8. 8 plus 3 is 11. 11 plus 3 is 14. How many edges do we have? We've got 1, 2, 3, 4, 5, 6, 7. The loop is 1 edge. Okay. The degree, or the sum of the degrees in a network, is double the number of edges. Okay. Very, very important, that one. And that's a very useful rule, that one. It's actually called the handshaking lemma. We don't need to know that particular term, but it's almost like if you're shaking hands with somebody, there's 2 people involved, but there's a single handshake. So just something there just to sort of keep in mind. Okay. So let's move on then, and I'm going to use a different board now. Okay, so we've talked about the degree of a vertex. Okay, actually no, before I do that, one other thing I'd like to, actually I'll use this diagram one more time. We talk about the concept of a walk, a path, and a closed path. So again, sorry, I'm just going to use a different color pen here. Okay, so we have a walk, walks, okay, paths, okay, and we have closed paths. Okay, closed paths are called cycles. Okay, we'll see why. When you talk about a walk, okay, a walk is basically any journey from one vertex to another. Okay, probably you can define it to be whatever you like. So a walk could be, for example, A to B to C to E, back to C, back to B to D, around the loop, back to B, back. I mean, a walk could be whatever you like. Okay, any journey from any one vertex to any other vertex, even back to itself. Okay, so a walk, there's no rules attached to how you travel around this network. A path, however, does impose a limitation. So a path is any walk that has no edges repeated and no vertices repeated, in fact. In fact, by not repeating the vertices, you're not repeating the edges anyway. So an example of a path would be, for example, A, B, D. So I might just put the examples here. Right. A, B, D. A, B, D, no vertices are repeated, and obviously no edges are repeated either. Okay. What's another example of a path? Can you identify another example? What about E, C, B, D? Okay. BAC. Okay. BACB though, or is something that is a little bit different. Now, yes, we've only used the edges once, but we have repeated the start and end vertex. That's called a closed path. Okay, so this term here, a closed path is a path that starts and ends with the same vertex. Okay, a regular path, notice, for example, e.g. A, B, D, the start and end vertices are different. So starting at A, ending with D. A closed path, however, is starting and ending at the same vertex with no edges or other vertices repeated. So using this diagram, okay, we can see that there's a cycle BAC. BAC, but then back to B. Okay, so starting at B, going through AC, so there's our path, but then to close the path, we have to go back to B. That's why it's called a closed path. It's closed up. It's like a shape that you can color in, and you can sort of fill it with color, or sort of forms a shape that you can sort of fill it with something if it was a container. If it was open, well then it can't be filled. So now I'm ready to use another board, of course. So, and I'm just going to continue on with our just our terminology. Okay, so we have two other or three other concepts that I want to go through before I finish the video on part one. And first of all, this is the concept of what we call a connected network. So far, all this is just terminology. So an example of a connected network, okay, would be, and I'm just drawing, this is all just random, sort of random vertices. Okay, so there's an example of a connected network. A connected network means pick any two vertices. Is there a way to get from that vertex to the to those two, between the vertex you pick, the first vertex, to the second vertex? In other words, if I picked vertex A and vertex C, is there a way to go from A to C? Yes, of course there is. That's not always the case though. Okay, so this is what we call a connected network versus a non-connected network or unconnected. Okay, and an example would be, and I might, okay, so for example, I might actually draw a very similar network to the first diagram. So, and I might just do that, and okay, there's our closed path, there's our cycle there. And I'm going to join A to E, but something happened. ED, I mean, there could have been a road closure or something. This is a non-connected network. In other words, if I chose the same two vertices, A and C, is there a way to get from A to C? And you can clearly see here, there's no way we can get from A to C. So this is really two sub-networks, okay, or two smaller networks that form obviously a larger network, but it's sort of in two pieces, the two unconnected pieces. So this is the concept of a connected network, and that's actually very important in further applications of networks where we have to assume or we have to deal with networks that are connected, and if they're not connected, that can complicate things obviously, and certain things just won't work unless they're connected. Okay, then we talk about the concept of a directed network. Okay, so far everything that we've looked at, we've assumed that you can travel in two directions. So in other words, we could travel either from A to E or from E to A, okay, or from E to D, for example, or from D to E. There's no direction stated. We could talk about a directed network, okay, and a directed network is exactly that. They're like one-way streets. So I might just use the same diagram, or very similar diagram to what I've done in the previous examples. Okay, and there's B, and this time round, I'm going to put arrows. All right. So, okay. So this is an example of what we call a directed network. In other words, the flow is indicated by the arrow. Okay, we can go from A to E, but we can't go from E to A. All right. We can go from E to D, but can't go from D to E. That's not allowed. We can go from D to C, fine. C to B, fine. B to D, fine. So that's fine. And that's a directed network. So that's where the arrows show the direction. Okay. We also have the idea though, and we haven't spoken about this yet until now, where if these were roads, is there something to indicate how many lanes the road is? I mean, are they one 2-lane roads, 3-lane roads? Are they major highways? So we have this idea of what we call a weighted network. Okay, and okay, what draw our favorite little network diagram? Okay, and that's A, B, D, C, and there's B. Okay, I didn't put arrows on it, so it's not a directed network, but I could put numbers on the edges to indicate either a cost, or could indicate the flow, or how big the edge is, how much capacity it could carry. So these numbers could mean anything. Okay, so sometimes that could be a cost. For example, if I'm building a road network, or I'm building an electricity network, this could be the cost. For example, could cost me $3 million to build a set of transmission lines from A to E, $5 million from E to D, and so on. Okay, so this comes in very handy when there's multiple ways of getting from one vertex to another, and we have to minimize the cost. Okay, because that's one of the applications of networks is cost minimization. Can we combine directed networks and weighted networks? Of course we can. Does that mean that because the arrows are there, we can't have numbers there? Oh, you can have numbers there as well. So if I was to draw a directed weighted network, okay, sorry, I'll just put that there so you can see that. All right, just bear with me. Sorry, I'll just get that focused again. Yep. All right. So again, I'm just drawing a. Alright, yeah, I could have arrows, okay, and I could have weights as well. So 3, 5, this could be 8. I'm just coming up with some random numbers. Okay, so this is a weighted directed network, or a directed weighted network. Doesn't really matter, so I'll just use weighted first. Okay, so this is a weighted directed network. Okay, so hopefully the terminology, and you're welcome to go through the video a few times, and sometimes it can take a few goes to kind of get used to the terminology. Okay, so a quick recap. All right, just quickly go back to this board here. Okay, the first and most important thing, what is a network? Bunch of objects and their relationships, okay, and the relationship between them. The objects are called vertices, okay? The connection, or the relationship between those objects, okay, is called an edge. Okay, so that's really networks 101, all right? Then we start to get into a bit more detail. Loops, multiple edges, degrees, okay? How many connections, or how many connections go in and out of a vertex. We talk about the relationship between the degree, or the degree of a network, okay, and the number of edges in that network, or the sum of the degrees. We saw that the sum of the degrees double the number of edges. We talk about the idea of walks, paths, and, sorry, I'll just write that again, closed paths, which are called cycles. Okay, so then we just spoke about connected networks, non-connected networks, directed networks, weighted networks, and weighted directed networks. This video is on network basics, and this is part 2 of the network basics series. And I'm focusing in this video in particular though on the table or matrix representation of a network. So if we can actually express the relationship between the vertices, or between the objects, using a table, or a two-way table. So here's an example to begin with. If you look at the top row and the left-hand column, you can see that the vertices here are labeled, and anywhere in the table that shows a 1, that shows that there's a connection between these two vertices. So for example, between A and B, there's a 1 there. That means that there's a link between the two. Notice that this is not a directed network. In other words, the connection from A to B is the same as the connection from B to A. So you can see that these two ones there, basically it's symmetrical across a diagonal. Okay, there's a connection from A to D, which means that it's the same connection from D to A. So this one is an undirected, unweighted network. Okay, so let's draw it. Okay, so what I'm going to do first is I'm going to draw 4 vertices. Okay, it doesn't really matter where you put the vertices, as long as you try and I guess put the vertices in such a way that you don't have too many edges crossing over each other, because it can get quite messy. So let's start off. So I'll go row by row. So on the first row it shows, as in when I say first row, the first row of the table that shows the connections. In the first row we've got AB, AD. Okay, so there's a link there. So AB and AD. Okay, second row. Okay, now BA, that's already listed, so that's okay. We've got BC. Okay. Okay. Third row, CB. Well, that's this connection here, so that's already been done. And last one is DA, and that's already done. So this network, or this graph, when I say the graph, it's just the diagram, is the representation of the network in table form. So these two are networks. This is what we call table form, or sometimes called matrix form, but table form is a more common term. This is what we call the graph form. Okay, both of these representations represent the same thing. Okay, it represents the same relationships between these sets of vertices. Okay, but one is drawn as a diagram, one is in a table. Let's have a look at another example. Okay. Could we express a directed network or a weighted network the same way? And of course we can. With a directed network, if you remember, directed networks have the arrows. Looks like that. Okay, so let's repeat the same process. I'm just going to just put dashes where there's no connections there. Okay, now notice that also there's a from and a to. Okay, so the column is the from, the row is to. So I've used different colors as well. So we're going from the reds to the blues. Again, there's 4 vertices, so I'm just going to draw the 4 vertices. Okay, probably just in a square pattern. A, B, C, D. Okay, so the first connection is from A to C in that direction. Okay, so from A to C and arrow. Okay, and there's nothing else. Okay, from A to anywhere else. Now we have a connection from B to A. Okay, so that's going back, B to A. Okay, the way you speak it is that gives you the direction of the arrows and the direction. So basically, the statement when you say from B to A, well, it's exactly in that direction. So you put the arrow accordingly. We have from B to D. Sorry, now I'm going to draw a. Okay, yes, they don't have to be straight lines. Okay, they can be curves. So from B to D, there is a connection as well. Okay, now we have the C, from C, we have C to B, there is a connection. Okay, and in that direction. Now, we have one from D to A. Okay, so going back this way. Yep, and we also have one from D to C. Okay, so this way as well. All right, and that would be the graph representation of the network that's originally in table form. Let's have a look at the weighted network. Okay, so same thing. This is a weighted network. It is not directed, so there's going to be no arrows. There's no from or to. Again, let's draw our 4 vertices. Okay. You can pause the video at any time. Probably should have said that earlier, but you can pause the video at any time, of course, and just have a go at these for yourself, and then just compare your work solution to my work solution, and just see if it looks somewhat similar. The vertices might be in different places, but the relationship should still be the same. And it wouldn't hurt to maybe every so often just make sure you practice this. You're welcome to replay the video at any time, of course, and that's why these videos are being produced. So, okay, let's do the same thing again, like what we've done before, A, B, C, D. Now, what you notice is that from A to A, there's an edge here that's worth 3. Now that means then, what do you call an edge that starts and ends at the same vertex without going to any other vertices? All right, it's called A, begins with L, called a loop. All right, so there's going to be a loop, okay, like that. Okay, oops, I shouldn't have put an arrow there. We'll get to that one where we have weighted directed networks. Yes, that's possible. So there is a loop there at A. We have, there's, so did I say 3? No, it's a weighted network, of course. 3, A to C, we have a connection and it's worth 2. Okay, so notice that you have to put now the numbers on the edges. All right. Make sure no arrows, all right? So it's a weighted network, not a directed weighted network. If it says from and to, then obviously you'd have to put the arrows in. And the last example we'll do will be a combination of both. All right, let's keep going. B to C, we have an edge worth 1. Yep. And we also have B to D is worth 5. So I might go around there. And that's worth 5. C to A. Okay. Edge, that's already there, it's 2. C to B, that should be the same. Notice that it, again, across the diagonal, okay, 1, 1, 5, 5, 2, 2, it's the same thing. So you can even just look at 1/2 of the table and that should be enough. I think that's it. D to B is worth 5, we've got that one already. So yeah, you can confirm just to make sure that all the edges are there. It's not directed, so it's not like you have to put an edge back the other way. And I think that's basically it for that one. Yep. Nothing else there. No. Okay. Last example where we will look at a weighted directed network. So that's our last one there. But then we'll look at another example where we have a graph and we want to produce a table. So we'll leave that on at sort of very last. So weighted directed network. Okay. Let's draw 4 vertices. Okay. A, B, C, D. All right. Okay, now we need the arrows and we need the weight, or sort of on each on the edges. So from A to B, okay, arrow this time. All right, A to B, that's worth 1. Okay, its weight is 1. And we have A to D is worth 3 in that direction. Okay, there's no symmetry necessarily around the diagonal. Okay, so it's only for undirected networks that the connection in 2 directions is the same. So A to C, C to A should be identical. You'll notice here that they're not in a directed network. Okay. All right. So that's the connection from A to anything else. Okay. What about the B's? So from B to C, there's a connection there, an edge. Okay, in that direction, and it's worth 7. A to D, sorry, was worth 3. We also have B to D is worth 5. Yep. All right, now that's it for the B's. So what about the C's? So C to A, okay, is worth 3. So we've got to go backwards. Okay, that's worth 3. Okay, now we have D to A. Now it's kind of like it's a multiple edge in a sense, but but they're in 2 different directions, so they're actually separate. Okay, so D to A, what was it, 10? So we're going to go, I might just do it on the outside actually. So D to A in that direction. Whoops. Okay, and that's worth 10. And D to B is worth 2. Okay, its weight is 2. Okay, and that would be an example of a network diagram or network graph that represents this particular table. Now your vertices could be in all over the place. It could be, I could have labeled these differently. It might look totally different, but the connections are still identical in terms of the relationships between the vertices. Okay, last one. So let's say you were given a graph, okay, or a diagram, and you were asked to produce the table. Okay, so again, there's 4 vertices. So let's try to do this as quickly as I can. All right. Again, you can have a go at this. You can beat me to it if you like. All right. And one more. Sorry, I know the tables are sort of rough and ready. I'm drawing them fairly quickly. Okay, A, B, C, D, A, B, C, D. Okay, so there are 4 vertices. All right. So from A, we have a connection. So we've got A to B. Yep. There'll be a 1 there. Okay, it's not weighted and it's not directed. Don't have to put arrows, froms, or twos, or anything like that. All right. Okay, A to B, and we also got A to C. Okay, and there's nothing else there. Now, if A to B, if there's a connection from A to B, there's a connection also from B to A. So I'm going to automatically fill these ones in. A to C, it means C to A. There's a connection there too. Okay. There's no loops. Okay, so there's none of these things happening. Okay, so because there's no loops, the vertex can't come back to itself. So I'm going to put dashes there. All right, and let's have a look and see. We got the B's now. So from B to C, we have a connection, which means from C to B, we have a connection. And there's no connection from B to D, okay, which means D to B, there's no connection there. Now the C's, we have a connection from C to D, okay, which means from D to C, we have a connection. And there's our completed matrix or table that represents this graph, okay, or this network diagram in table form. In this video, we're going to talk about the concept of trees in networks, and in particular, spanning trees. And we need to do this before we look at minimum spanning trees and calculating or determining a minimum spanning tree using either Kruskal's algorithm or Prim's algorithm. So first of all, what is a tree? Okay, so they're not the biological kind. In fact, there is a relationship between a tree in a network and a biological tree. And there's a reason why it's called a tree. A tree is a type of network where there are only paths between any two vertices. Okay, so you need to think back to what is a path? What is meant by a path? A path is a special type of walk. Okay, in other words, there's only one way to go from one vertex to another. It's not multiple ways. Basically, what this means is that trees do not contain cycles or multiple edges. Okay, let's draw some examples of trees. So, as an example, if I was to okay, all right, okay, that would be a tree. All right. So, in other words, to go from choose any two vertices, for example, A and C, there's only one way to get there. To go from A to B, there's only one way to get there. Okay, so it's not like there's multiple ways of going between any two points. Maybe let's draw another. So 1, 2, 3, 4, 5, and what we might do is I might draw that there, and that there. Okay. Now, in fact, sorry, I should just probably put that E there. Yep, maybe make that E. B up there, C and D. Okay, 5 vertices. Is this still a tree? Yes, it is. It's not a connected tree though. Okay, so remember we talked about connected and unconnected or disconnected networks, okay, or non-connected networks. This is an example of a non-connected tree. In other words, there's only one way to go from A to E. Sure, we can accept that. But there's no way to go from A to anywhere else. However, to go from B to C or B to D, of course, there's only one way to do that. So this is still a tree, okay, but it's not what we call a connected tree. Now you should probably start thinking about, well, where does the word spanning come into it? Okay, so these kind of networks, these kind of trees, we don't consider. Now, if you take a biological tree, as I know I did mention a biological tree earlier on in the discussion. In fact, if I drew a biological tree, what would a biological tree look like in terms of a network? In fact, could we model a real tree with a network? Well, probably. Okay, that could be the roots. Okay, and there's probably the trunk, and there may be several branches. Okay, coming out of the from the trunk of the tree, or from the main stem, or okay. So I might just put vertices there. Okay, this is also a tree, because if I was to label, in fact, just maybe do one more there, just because I can. If I was to label all these vertices, E, F, G, H, make that I, J, yep. To go between pick any two vertices, there's only one way to get there. So every walk is a path. Okay, there are no cycles. There are no multiple edges. You can't have this either. Okay, so we can't have this sort of situation. So let's say okay, that's a tree, but you can't have this. Okay, that's a multiple edge. Okay, so that is not allowed. In other words, it's not a tree. It's something else, but it's most certainly not a tree. Yes, it's a connected network, but it's not a tree. Okay, so the emphasis is on a tree and that particular type of representation. Okay, all right, let's have a look at the next slide. Okay, this is where we talk about spanning trees. Now that we know what a tree is, a spanning tree is a connected network. Okay, we can't have this situation where there's two subnetworks and there's a break between them. So there's no way to get from one part of the network to the other. So it must be a connected network. And again, the same rule applies in terms of the definition of a tree. There can only be paths. There's only one path between any two vertices. In other words, there can be no multiple edges and there can be no cycles. Okay, so examples of spanning trees. So if we had four vertices, okay, for example, I might just label these A, B, C, D. Okay, A, B, C, D. Okay, pick any two vertices. There's only one way to get from that vertex to another. So to go from A to D, the path will be A, B, D. To go from A to C, it can only be A, B, C, for example. So it's not like there's a cycle, or you can take two different ways to go from point A to point C. Okay. Notice that between these two diagrams here, okay, the edges are different in terms of their placement, but it's still a tree. So there's multiple spanning trees that are possible given any network. This one here, so this diagram at the bottom here, this is not a tree, okay, and it's not a spanning tree for that matter. Because it's not a tree, it's not a spanning tree. So why is that? Because we have a cycle. Okay, so this BCD, okay, this cycle there stops it from becoming a tree. Okay, yes, it's a connected network, but it's not a tree. So if it's not a tree, it can't be a spanning tree. Okay, so if a tree is not connected or disconnected or unconnected, there's multiple ways of saying that, I guess. So I might actually go back to this slide here. Okay, so if you remember this diagram, actually I'll just draw a different one. Okay, so if we had that there, okay, this is a tree, but it's not spanning. Okay, it's disconnected or it's unconnected. Okay, so for a tree to be spanning, there has to be a way to go from between any two vertices. Pick a vertex. There's got to be a way to get to every other vertex. Okay, or else it's not a spanning tree. It's a disconnected tree. Okay, so hopefully we've defined spanning trees. We'll go just one more point though on spanning trees. Okay, a network can have many spanning trees. So if you have this network here, okay, we'll take our famous four vertices, A, B, C, D, in that square. There's no fifth vertex, so these edges that cross over, there's no vertex in the center. How many spanning trees are possible? First of all, this particular diagram is not a tree. Okay, it's sure it's connected. Sure, there's ways of getting from between any one vertex to another. But there's cycles and sort of too many cycles here, and it's just not going to work. So in fact, if it's got one cycle, it's no longer a tree, so it can't have any. But there are several possible spanning trees. We've already seen some, so we could have, in fact, you might want to think about how many different spanning trees, in fact, are possible with this arrangement. We could have, there's one possibility, okay, so A, B, C, D. That's one possible spanning tree. Okay, we could have another. Okay, we might have seen some in a previous example. I think it was on the previous board slide. So we could have like that. Okay, B, C. We could have something like that, and the list goes on. So you could probably draw them all out, in fact. But here are three possible spanning trees for this network A, B, C, D. Okay, so yes, there's more than one. All right. Now, one last note, and I think it's really good to note this. Look at all these spanning trees here in green. We've got 4 vertices. How many edges are there? Each one of these diagrams, okay, each one of these spanning trees has 3 edges. So if you were to, for example, have a 5 vertex network, how many edges would it take to make it a tree or a spanning tree? Okay, so one thing to note is that a spanning tree has 1 less edge than the number of vertices. Okay, so therefore, if there are n vertices, there are n minus 1 edges. If there's 10 vertices, there'd be 9 edges. Okay, 5 vertices, there'd be 4 edges. Let's prove the point. Okay, at least with five vertices. In fact, why don't we go 6 vertices? Okay, so let's draw a spanning tree. Okay, we could even have a star set up, for example, but I'll do something like this. Okay, would you agree that this is a spanning tree? There's no cycles, there are no multiple edges, there are only paths, and all the vertices are connected. Okay, so this is a connected network, and it's a tree, therefore it's a spanning tree. Right, how many edges do we have? 1, 2, 3, 4, 5 edges. Okay, if you add another vertex, you need to add another edge somewhere. Okay, there you go. So there's 7 vertices, 6 edges. Add another vertex. Okay, we need to add another road. So basically, every time we add a vertex, we have to add an edge. In fact, the simplest, absolute simplest spanning tree that we could have that involves at least 1 edge is this one. Okay, 2 vertices, 1 edge. Every time you add a vertex, you have to add an edge. Add another vertex, add an edge. Okay, and the pattern continues. So that's another very useful, a very useful little fact in networks, and especially with spanning trees. In the next video, we're going to look at minimum spanning trees. So if we give these weights, for example, or give a network a weight, in fact, just bear with me, I'm just going to about the board. Okay, so just to show you what I mean, so let's draw our famous 4 again. A, B, C, D, and okay, this could be, these edges could represent, for example, the cost of building a road in millions of dollars. Okay, 45, let's say that's 3, let's say that's 5, and let's say that's 17. What would be the cheapest road network that we could build that connects town A, town B, town C, and town D? And that'll be explained in the next video. Thanks for watching. In this video, we're going to build on our understanding of spanning trees, and in particular, a application or an application of spanning trees where we come up with a network that links all the vertices together, but with the minimum cost. Okay, and I think this is best done by example. Okay, so what we're going to do is let's have a look at this example here, and what we're going to do is we're going to link all 6 vertices together in such a way that it's a tree. A tree uses the minimum number of edges. Okay, so in other words, if we've got 6 vertices, we need to pick 5 edges. If you remember that rule from the last video, okay, so if you have 6 vertices, there's 1 less edge, okay, and that'll form a tree. And also remember the definition of a tree. A tree is the minimum, basically the minimum number of edges needed to link all the vertices, okay, in such a way that there are no cycles, multiple edges, all that kind of thing, right? So just a simple network with the absolute bare minimum of edges to link the whole thing together. So we could think of these vertices A, B, C, D, E, F. We could think of them as towns, okay, or cities, whatever. And we can think of the edges as roads. Now, what we see here is clearly not a tree. It's a tangled mess, probably one way to describe it. Cycles everywhere. I don't know if there's any multiple edges in this one. Maybe not. I don't think there's any multiple edges here, but there's most certainly lots of cycles. Okay, that's not a tree. We need to basically extract from this diagram 5 edges. Okay, 6 vertices. We need to pick 5 edges of minimum weight. Let's pretend these numbers. Okay, for example, if they're roads, let's say we're building roads, okay, between these cities or these towns, and the numbers indicate the cost of the road, for example, in say millions of dollars. We want the cheapest road network with the minimum number of roads needed to link all 6 of these towns together. And we're going to use an algorithm here called Kruskal's algorithm. Kruskal's algorithm is actually probably one of the most straightforward ones. All we need to do is pick the edges or start choosing the edges that are of minimum weight. And then you start to go to the edges of higher and higher weights until you end up with the tree. Okay, and that's it, and then you stop. So what we're going to do first is we're going to, I'm just going to draw the solution just here on the side. So I'm just going to basically redraw the vertices. Okay, so there's A, B, okay, so try to keep it somewhat to scale. Or at least put the vertices roughly where corresponding with the original diagram. I think F was somewhere here, okay, and C was somewhere in the middle. Okay, let's start. Let's have a look at the edges in the original diagram, which identify the edge of absolute smallest weight first. Okay, so looking around, you can do this by inspection. You can see that edge CE has a weight of 1. Okay, so, and there's no other 1s anywhere. So when you find the edge of minimum weight, see if there's any others that are the same. So there could be other 1s there as well. In fact, you'll notice that when you go to the 2s, there's 2 of them. In fact, yeah, there's 2. I thought there might have been 3. No, there's 2 there. So let's draw in CE first. Okay. Right, so now we've linked town C to town E. Okay, it's okay. So we've connected 2 of the towns together. Let's go to the next weight up. So there's no more 1s. We've got roads of cost of 2 or weight 2. We've got BD, that's a 2. So let's connect that up. Now, by the way, I could have chosen CF. And I may just do so next, in fact. I'm just going to put the weights there. So that's 1, that was weight 2. Notice though that by connecting B and D together and then C and E together, that what I've done is I've formed a part tree, really. There's 2 paths, clearly, but it's an unconnected or a disconnected network. It's not a spanning tree. It's a tree, but it's not a spanning one, okay? It basically, Kruskal's algorithm just picks edges randomly as long as the edges are of minimum weight. That's the only condition. Okay, so BD's there, CE's there. Okay, now we've got FC. Okay, sometimes what I do is I could put a dot or something there to say that I've used that edge up. Okay, so let's use the next edge, which is FC. Now the other thing as well, that as you're picking these edges, you must not form any cycles. That's a no-no, okay? No. As soon as there's a cycle, basically it's all over. It is not a tree, it is incorrect, okay? So be very, very careful that, for example, you don't pick, for example, FE. Oh, there's a number missing on that. And I might just put maybe a 3 there, just to make it interesting. You'll see why shortly. You cannot choose any edges that then form a cycle, okay? Because that's not a tree. All right, so we've used that 2 there. Now, the next edge or set of edges that we can pick, one up from that, we've got 3s. So we've got a 3 there and a 3 there. Now, FE, okay, can you choose that? If I was to put FE there, let's say I might just draw it apart there. Is that permitted? Yes or no? And hopefully you've said no, it's not permitted. Why is that? Because you've got a cycle. And once you have a cycle, it is no longer a tree. It's a spanning network, but not a spanning tree. You know, it's got to be a tree. Trees are the absolute minimum, okay, of an absolute minimum network that links all the vertices together. Remember that. So this one we cannot pick. Okay, we can't pick that one. That's gone. However, there is another 3 that we can choose. We can choose AB. That's okay, because that doesn't form a cycle, okay, or a closed path. And that's worth 3. Okay, we have quite an interesting network here now. So what we've got 4 edges, and it's a disconnected network, but we've got towns A, B, and D linked together, F, C, and E linked together. Now, if this was an actual road network, let's say this, that we had people building these roads, as they're building the roads, it's like they're building 2 sections and they're disconnected from each other. So during construction, there's still no way to get from A to C, for example. Okay, so it's like there's 2 trees slowly sort of coming together, and eventually they'll link up and it'll form one big tree. Okay, that's how Kruskal's algorithm works. It's kind of just, I wouldn't say haphazard, but you're kind of just picking edges all over the place, and of minimum weight. So now we've used that one there, so that's good. Any other 3s that you can see? No, that's good. No 3s. Okay, 4s. How many 4s do we have? Okay, we've got this 4 here, and there's no other, so we can choose that one there. And what do you think? We stop? I think so. I think we can stop there. First of all, 6 vertices, we have 5 edges. We also have a tree, okay? And we can get from any vertex to any vertex that we want, okay? There's a path from between any 2 vertices. We have formed a tree. We have formed a spanning tree. In other words, it is a connected network. Now, what's the weight of this network? All right, we add up all the numbers together. Oop, and I forgot to put in AF, so that's, sorry, that was a 4. That was the last thing I did. Right, let's add these numbers together. Okay, 1 plus 2 is 3, 3 plus 4 is 7, 7 plus 3, 10, 10 plus 2, 12. Okay, so I'm just going to add them all together, all the edges together. 1 plus 2 plus 4 plus 3 plus 2, which equals 12. And that is the weight of this spanning tree, of the minimum spanning tree. Okay, so next video, we're going to look at another algorithm that produces a minimum spanning tree, so the tree of minimum cost, but it uses a slightly different method. Okay, so, and it's called Prim's algorithm, and I'll be doing a video on that next. Let's look at another algorithm that's used to generate the minimum spanning tree. In the last video, we looked at Kruskal's algorithm, and Kruskal's algorithm basically just picks the edges of minimum weight. So, you know, we might pick the 1 and you know, they might pick the 2 here, and basically it just picks edges from all over the place. And it actually starts to build a network that might appear a little bit disorderly at first and all disconnected and disjointed, but eventually all comes together nicely in the end to form our minimum spanning tree. So it's possible then to get from any vertex to any vertex. So Kruskal's, you can think of Kruskal's algorithm as a little bit disorderly and a little bit haphazard in that it just picks edges from all over the place. Sometimes though, we want to build a minimum spanning tree where the tree actually grows as if it's growing from the roots all the way to the top. And there's nothing disjointed. So you don't have an edge here or an edge there or an edge here, but it actually grows the edges basically from a source or from a starting point until it eventually all the edges basically connect everything up. And that's sometimes the algorithm that's used, for example, to build internet networks, for example, electricity networks. It kind of doesn't make sense to put a wire from, say, B to D, I might just draw it in there, and then say from, you know, F to E, but the generator's at A. It is counterintuitive, isn't it? It sort of doesn't make sense. It makes more sense though that from wherever the generator might be, you start to grow the network from the source. Okay, so it's also for traffic as well. So let's just say that there's a major city and we want to connect that major city to some regional towns. It probably makes sense to build the road from the major city first and then slowly start building it out until it eventually encompasses all the towns, okay, that are there. So let's have a look at Prim's algorithm. So Prim's algorithm, okay, like I said, it's a bit more orderly. We need to pick a starting vertex, and it doesn't really matter which one you choose. You choose any one you like. In the end, we're going to build a minimum spanning tree. A tree means that every one of these vertices have to be connected eventually. So pick whichever one you like, and we can start from, I don't know, let's just start from A, because we can, and A is the first letter of the alphabet, so we might as well start there. So the way it works is this: we pick our start, okay, so let's say we're starting here at A, okay, so we're going to start at this vertex here. So it works by vertices, not so much by edges as Kruskal's algorithm does. Starting at A, let's have a look and see what edges join to A, or connect to A. We have this edge here, AF, which is worth 4. We got AE, which is also worth 4. AC is worth 8. AD is worth 6. AB is worth 3. You pick the smallest. Okay, so like Kruskal's, we still got to pick the smallest or the lowest weight edge, or the lowest cost edge. Okay, so we're building. Let's say we're building a road network. We pick the lowest cost. So starting from A, the lowest cost edge is 3. Okay, and we might as well, so we're putting the weight there and sort of start to build our tree. Now what we do is from A and also from B, okay, we're going to start building our tree now from one of those two vertices. Because now we've connected A and B together, we can't connect E and D now. Whatever we start to draw has to build on the original tree that we've started. We've started the tree here. The next edge we draw has to come from either A or B. Okay, it's very important that as we build our network, it must remain connected all the way through. That is the reason why we use Prim's algorithm over Kruskal's algorithm. If you ever get a question that states, why would you use one algorithm over another? They're not just two random algorithms or just two things that work. There is a reason why we would choose Kruskal's. There is a reason why we would choose Prim's algorithm. That is very, very important. Okay, back to this. From A, okay, what other edges have we got? We got a 4, we got a 4, we got an 8, we got a 6. Okay, you could list these down somewhere if you like. It's up to you how you want to do the accounting for this, or you can do it by inspection. That's fine. Now from B, we have a 7. Okay, we've got a 9, we've got a 6, we've got a 2. Out of that set of edges, or that group of edges I just called out, BD would be the smallest. Okay, so let's put that in. Okay, and that's a 2. Okay, now the next edge that we're going to select has to either connect to A, has to connect to B, or D. Okay, again, we're building our tree. Again, Kruskal's probably not very happy here, going, oh, hang on a moment, but there's a smaller edge out here somewhere. No, that's a different algorithm. Prim's saying, no, we've got to maintain the tree, okay, and maintain the connectedness of the tree. Must remain connected as we join on these roads, okay, or these edges. All right. So from A, what edges have we got? We've still got the 4, we've still got the 4, we've still got the 8, we've still got the 6. Now we can't choose the 6 because that obviously it's bigger than what other choices we've got. Plus it forms a cycle, so that sort of rules that one out now. So we can't actually, the 6 is actually gone because it forms a cycle if we join that. From B, we've got a 7, we've got a 9, we've got a 6. Now the 2 is already taken up. Okay, so now from D, we've got a 6, we've got an 8, we've got a 5. Okay, so I think the one that we're going to use this one here, the A, which is the 4. Okay, which is going to connect up to vertex E. Okay, sometimes, or there's another 4 here that we can use as well. Actually, we have two choices. We've got AE or AF. It doesn't really matter. In fact, you may end up with a different shape minimum spanning tree from the last example that we did with Kruskal's, but the minimum weight should still be 12. And that's what we got in the last example. So let's compare. Okay, which one do you want to choose? Doesn't really matter. I think maybe we'll just connect A, E together. How's that? All right. So we'll do that. Okay. And that's worth 4. Okay. Right. So far, what's the weight of this network? 2 plus 3 is 5. 5 plus 4 is 9. All right. Now, we've got more choices. We need to choose 2 more edges. Okay. So we need to connect F and C somehow. Okay. Now, from E, we can see that there's an obvious choice. We've got a 1 here. Okay. There's no other 1s anywhere else. So from E to C, that is the obvious choice. Okay. And that's a 1. Notice that every edge that I've chosen, that we've chosen so far, every edge that's chosen has built the tree and has maintained it in a connected state. In other words, as we're building a road, it connects all the other roads with it, not all separate, disjointed all over the place, and then finally the final road goes in that then sort of connects the whole thing together. All right, we've got one more edge to choose. Okay. Again, looking at all the choices that we have, and Prim's takes a little bit more time because you have to consider all the different options. And as you start to build these roads, you have to start thinking, well, what's the smallest edge I can choose that connects to all of these vertices? Because you have to consider all the edges that come off all the vertices that we've connected so far. Now, we do have a fairly obvious choice here. Okay, we've got FC, which is a 2. There was another 2 somewhere else, which is BD, which we've already chosen that one, so we can't pick that again. That's useless. But connecting F, we've got AF, which is 4. We've got FE, which is 3. We've also got FC, which is 2. Now, I could just build it. I could just put it straight across. In fact, I might just do that. Or I could sort of draw it around. In fact, how about I do that? Okay, you can. Doesn't change the network at all. It's still worth 2. Okay, or I could have just drawn it across. Doesn't really matter. Okay, right. Let's see if we got the minimum weight of 12. Okay, let's add up all the weights. So the minimum weight of this network. Okay. Okay, of this spanning tree is equal to, what have we got? 1 plus 2 plus 2. So what's that? That's 5 plus 3 plus 4. That'll be equal to 12. So we end up getting the same weight as the example that we did using Kruskal's algorithm. In fact, we ended up even getting a different shaped network. Okay, so the different roads that we've built, we've actually chosen some, maybe I think we've chosen 1 or 2 different edges, but we end up still with the minimum weight. In other words, the cost of building this network is exactly the same as building the network that was determined using Kruskal's algorithm. Okay, and that's how Prim's algorithm works. So always remember, and I think probably the take-home point from here is, why would you choose one algorithm over another? Okay, Kruskal's is less complicated, but it tends to be a bit more haphazard. It does not maintain the connectedness of a network as you build it. Prim's, on the other hand, does. So Prim certainly does have an advantage over Kruskal's just in that point alone. I'm just going to introduce the basics of shortest path, and it's going to form really the basis of shortest path problems in networks. And I guess where this comes from is situations such as getting from sort of one point to another, or traveling from one point to another. So for example, between home and school, or home and work, there's more than one way to get there. So you might find that the main road to get from, for example, home to work, there might be too much traffic. So you might think about taking another way, or maybe some back streets or something like that, to save the time. I mean, it might be a greater distance, but it still might, you might be able to get to work a lot quicker. So this is really about considering the cheapest way, the shortest distance, shortest amount of time, whichever way you want to look at it. That's the basis of shortest path problems. Okay, but the way we're going to start off though is that let's just consider this network here. all we're going to do is that we're just going to find the shortest path between vertex A and just every other vertex. Okay, so we're not being specific as to any particular vertex here. Okay, so what we're going to do is it's a bit of an algorithm that we're going to go through. Starting at vertex A, okay, let's consider the vertices that are closest to A, so one edge away. So we've got vertex B, vertex C, vertex D, I guess. So we can do these one at a time. So we want the shortest path. So the path from A to B. Okay. We need to consider all the various ways we can get to B. We can get to B directly, so from A to B. That's a cost of 2. We can get to B via D, so we can go A, D, B, but that's a cost of 10. So certainly that's not the shortest path. When we say shortest path, it doesn't matter how many edges we choose. It's the sum of the numbers, the sum of the weights on the edges that matters. Okay, so sometimes we fall into this trap thinking, oh, but I've taken too many edges to get from one vertex to another. That doesn't matter actually. What matters is the cost or the weight of the edges. The sum of those has to be the minimum, not the number of edges. Okay, so can you just make that one point very clear. Okay, so from path to A to B, from just by inspection. Okay, I'm just going to put the weight of the path or the weight of the path from A to that vertex that we've chosen. I'm just going to write that up in green there. Okay, what about say vertex C? Vertex C, we've got a direct path there from A to C, and that's 5, well, it costs 5. I call it a cost, sort of a cost in time, a cost in money, or a cost in distance, or some other cost. So that's 5. We can go to C via D, but I don't think that's going to help us here, so that's 11. There's so many other ways you can get there, but some of these other paths are just ridiculous. We don't even consider them. I mean, the value that you're going to get when you add up all the numbers is going to be too high. So we just consider the most reasonable options. So A to C, well, probably just direct. A to C is just 5. Okay, so I'm just going to fill this in. So path from A to B, we get 2. Path from A to C, okay, is 5. Okay, what about D? Okay, so I'll give you a few seconds just to think about that. Okay, think about the various ways you can get to vertex D, starting from vertex A. We've got a direct path, of course, that's going to cost you 7 units. We can go to D via C, so A, C, D, that's 9. But we can also go via B, so A, B, D, 2 plus 3, that's 5. So we want the shortest path. So when I say shortest path, yeah, sure, it's taken 2 edges, and 2 edges is obviously greater than 1 edge, but we don't care. Okay, so we don't count the number of edges. It doesn't matter. Just add up the values that make up that path. So from A to D via B, 2 plus 3, it's 5. Okay. So these numbers now that I've placed next to the vertices are basically the weight of the path from A. Okay, I'll just put that in a circle. From A to these 3 vertices. Okay, we've got 2 more now to consider. So what about path E, or the path to E from A? We've got 2 plus 7, so that's 9. There's another way that I can see. We could go A, D, E. Okay, that's 7 plus 1, that's 8. There's still a better way. Okay, D, to get to D only costs 5 anyway. So we can use what we've calculated before to help us find the shortest path to that vertex. It takes 5 units, or a cost of 5 to get to D via B, A, B, D. Add another 1 to it. It's the smallest, it's the lowest weight edge there. So 5 plus 1 is 6. So A to E, okay, the cost there is 6. Okay, now finally, to get to F, okay, we can get to F via either E or D. 5 plus 8 is 13, okay, or 6 plus 9 is 15. So clearly 13 wins out there. So A, to F, okay, is 13. So what we've done is that we've calculated the shortest, basically the shortest path, or the lowest weight path from A to each of these other 5 vertices. In this example, we're going to determine the shortest path from vertex S to vertex T, and that's actually why I put those 2 vertices, I've enclosed those vertices in circles, just so that we can see the start and end a little bit clearer. The numbers in red are the weights of all the edges, okay? So what we're going to do is we're going to come up with a path, or try to determine a path from S to T where the weight of the path is as low as possible. Hence why it's called shortest path, okay? The numbers could represent distance, for example, distance in kilometers, could represent a dollar amount, so the amount of money it takes to travel from one vertex to another. You know, it could be a time, so number of hours, for example. So we want to try and come up with a path that's going to take sort of the least amount of whatever it is that we're trying to determine, the lowest number. Now we can also see that there's so many ways of getting from S to T. Okay, we can go S, A, B, T, for example. That'll be 1 plus 12 plus 6, which is 19. We can go S, E, F, T, which has a weight of 24. There's S, C, D, B, T. I mean, there's so many paths, and to list them all can be quite arduous. You know, it could be there for a while, in fact. Just listing all the various paths from S to T. So we're going to take this a little bit more methodically and really attack this just with a bit more method to the madness, so to speak. So what we're going to do, we're going to consider the vertices that are 1 unit away from S first. Okay, so these are the vertices A, C, and E, and we're going to slowly sort of migrate over to T eventually. So to get from S to A, okay, the quickest way to get from S to A, and you have to consider sort of the roundabout ways to get to these vertices as well. From S to A, the quickest way is going to take 1 unit. Okay. From S to E, okay, we can either go S, C, E, but S, E is certainly the more direct way, but it's actually the way that's going to give us the lowest weight, or the least cost. That's 8. Now SC is 4. But you can see that it's also, to get to C, we can go via A. So SAC is in fact going to take 3 units, 1 plus 2. It's going to be quicker than it is to go direct from S. So I'm going to put the number 3 there. Now, this is where it can get a little bit confusing, and this is why, to help, to alleviate some of that confusion, I'm going to use now a different color, different color pen, to look at the vertices and to determine the weights of the paths to the vertices that are now 2 edges away, or the next set of vertices away from S. So now we're getting closer to T. So let's have a look at, for example, vertex F. We're going to consider the numbers in blue that are going to help us to calculate the weight of the path to F. So to get to F, we have to choose one of these 3 vertices. So from E to F, 8 plus 9, that's 17. We can go from C to F. Okay, so that's 3 plus 6, which is 9. So in fact, they're the only 2 ways to get to F. So that path there and this path there. Okay, 3 plus 6, 9. That's certainly the least of the 2 options. Now, to get to vertex D, we can either go AD. Okay, so 1 plus 7, which is 8, or we can go CD. Okay, also that's 3 plus 5, which is also 8. So we can put an 8 there. So they happen to be equal in length. That's okay. That can happen. Now, B, the only way to get to B is in fact via A. Okay. So 1 plus 12. Okay. Is 13. But you might say, well, hang on a moment. We could get to B via D. In fact, since we've just computed D, could we use D? Even though originally we're using the numbers in blue, could we then now use the numbers in green? Yes, you can, actually. In fact, 8 plus 3 is 11. So we can actually put 11 there rather than 1 plus 12, which is 13. Yes, it's a little bit more of a roundabout way, but it still gives us a lower number, okay, even though we're going about going about it a little bit less, a bit more indirect, I guess. Now, finally, we've determined that now that sort of these three vertices. Now to get to t. To get to t, we can either go via b or via f. Okay, so 9 plus 7 is 16. We've got 11 plus 6 is 17. So 16 is it. Okay. Hope that makes sense at this point. We still haven't determined what the shortest path is yet. We know what its weight is. We know it's going to be 16, whatever, 16 kilometers, $16, 16 hours, whatever. But let's now determine how to actually trace out the path, which is the shortest path. Now, starting from 16, okay, we need to now start backtracking. Okay, 16, and what you do now, you start subtracting the numbers in red. 16 minus 6, and it should equal the number that's next to the vertex. So 16 minus 6 is 10, but we have 11 here. So it's actually not, can't use this path, it must be this path here, because 16 minus 7 is 9. Okay, so what I'm going to do is I'm going to draw in the shortest path here in blue. Okay, now from F, 9, 9 minus 4 is 5, but we have an 8 here, so it can't be this one here. 9 minus 9 is 0, but we have an 8 here, so it can't be this one here. 9 minus 6 is 3, and it's most certainly this edge here. Okay, now from C, 3 minus 4 is negative 1. We actually want a 0 here because obviously you're at the start, so it's not costing anything. 3 minus 4 is negative 1, but we want a 0. So it can't be this edge here. Okay. 3 minus 2 is 1. Okay, so it looks like it's this edge here. And then finally, from A back to the start, 1 minus 1 is 0, and that works. In fact, what other choice do we have, really? But it's just a way to verify that we actually did the right thing. So therefore, the shortest path, okay, so this is what we did there was backtracking. So the shortest path is S, A, C, F, and T. Okay, and the weight and the of weight 16. Here's another example that involves coming up with the shortest path from S to T, okay, networks. So this one's a slightly more complicated version of example 1, okay, but we're going to do the same basic thing, right? The same basic algorithm to determine the shortest path from S to T. Again, we're going to consider the vertices that are one edge away from S first, and then we're going to slowly migrate sort of from S to T and consider the vertices further and further along. Okay, so the first two vertices to consider then that are basically closest to S are A and E. Now to get to A, it's going to cost 9 units. So I'm just going to put a 9 there above the A. And we try and think of if there's any other way to get to A that's might be a little bit, more indirect, but it may actually be a shorter path in terms of the weights. To get to E, in fact, the quickest way to get to E is directly to E, not via A or any other vertex. So we're going to put 12 there. Okay. So let's move along now to the next set of vertices. So we're going to consider vertex B, D, and F. Okay. Then finally we'll consider C, vertices C and G. Then obviously T is the end. Okay. So let's have a look at vertex B. So vertex B from A. Well, there's really no other way to get to vertex B. Apart from A, going to A, so 9 plus 5, it's going to give us 14. Okay, so that'll be 14 then. Okay, let's have a look at vertex D. Now, vertex D could be reached either from A or from E. Okay, so from A, 9 plus 15, that's going to give us 24, or D from E, okay, is going to be 22. So 12 plus 10 will give us 22, okay. We can either get to D from F, but we haven't even considered F yet. So why don't we work this one out now? So and put in the value of the weight of the path from S to D. Okay, so last one to consider now is F. In fact, to get to F, we can go from E to F direct, okay, which is 12 plus 12, which is 24. Another way to get to F is we could go via D, okay, so sort of indirectly, so E, D, F, again, adding 2, you end up with 24 as well, okay. So there's a little bit of, there's a little bit of trial and error, a little bit of, you sort of just have to look at it by inspection. There's so many possibilities of paths. If we were to list out every path, you'd be there for a very long time, okay, relatively speaking, okay. So this is kind of a, not pure trial and error, but it's a considered trial and error, is probably the best way to think of it. Okay, so we've got B, D, and F now worked out. So far, B is in the lead, okay, so to 14, costing 14 units to get there. D and F are certainly more expensive, but that doesn't necessarily mean that they're out of the race. Okay, so that's a lower number, that's the winner. Okay, let's have a look at vertices C and G. So to get to C, we can either get to C from B, or we can actually get to C from A as well. So 9 plus 13 is 22. 14 plus 7 is 21. 22 plus 8 is 30, so that's way off. So we can consider BC as probably the best path to take. So 14 plus 7 is 21. Okay, that's to get to vertex C. You're trying to just sort of look around C and think if is there a quicker way to get there, but there's no quicker way to get there. In fact, so what about vertex G? Okay, so vertex G, we can either reach G well from C, but C is already at 21 plus 14. We try and aim for the paths that obviously result in the lowest number. We've got D's already at 22. If we add 1 to that, you get 23. 24 plus 9 is 33. Well, that's way off. 22 plus 1, 23. Well, 23 has it. Okay, and that's definitely the better option there. Okay, and either way, if we go from vertex C to G, adding 14, well, that's 35. That's again way off. So this edge here is a very large number relative to some of the other edges. So finally, well, there's not much of a, well, it's not going to be very difficult now to determine which is the best path to T. We can either go from G to T, so 23 plus 10 gives you 33, or we can go via C. So C, 21 plus 2 is 23. Okay, so the weight of the shortest path is 23. So if it's a cost, dollar amount, it's definitely the cheapest. If it's a distance, then it's obviously the shortest distance. If it's a time, then it obviously takes the shortest amount of time. Now, the last thing we need to do is to quote the shortest path, as in the vertices that make up the shortest path. So we need to indicate those. And what we do is that we backtrack again. So we did that in example 1. So let's backtrack now. So 23. What we do is we start subtracting the numbers in red, and it should equal the numbers in blue if we've chosen the right path, going backwards. So 23 minus 10, well, most certainly it's not 23. And if you remember what last edge you chose anyway, that will most certainly make it a lot easier. So we've got that edge there. So 23 minus 2 gets us to 21. So the shortest path, so ending with T, we've got a C. Okay, from 21, so we can either go back to B, or back to A, or back to D. So 21 minus 8 is most certainly not 22, so it's certainly not that path there. 21 minus 13 is not 9, so that can't be that one. But 21 minus 7 is 14. Now again, if you remember that was one of the edges that you chose, it does make life a little bit easier. So going backwards, B is the next vertex. So from 14, well, there's no real option apart from going back to A. So 14 minus 5 is 9. So A is certainly along the path, so it's on the path. And 9 minus 9 is 0. Of course, the starting value is always 0, and therefore we now have our shortest path. So shortest path, therefore, okay, is SABCT, and the weight is 23. Here's another shortest path example, and we're going to go again from vertex S to vertex T. The numbers indicate hours of travel. So for example, to go from S to A is going to take 3 hours of travel. Okay, so let's do what we've done in the previous examples, and let's consider the vertices that are one edge away from S first. So in other words, from S, there's one of two vertices has to be in the path, basically. Either has to be A or G. So with A, getting to A is going to take 3 units, okay, or 3 hours, sorry. S to G is going to take 4 hours. So I'm just going to put the numbers here in blue. Okay. Now let's consider the vertices now that are sort of another edge away. Okay, so a bit further away now from A and G. So we've got basically the vertices that can now be reached from the vertices that we've worked out. So we've worked out A, we've worked out G. So let's consider the vertices that are now reachable from A, namely B, E, K, and H. Okay, and so let's from A going to B, A is 3 hours plus 6. That gives us 9 hours. Okay, 3 plus 5. Okay, so going now to vertex E, 3 plus 5. That gives us 8 hours. Okay. Now to K, we can either go via A, so A to K is so 3 plus 4 is 7, or we can go via G. So G to K is 4 plus 5 is 9. So 3 plus 4, 7. So we choose the lower of the two values. And H, we can either go via G, so G to H, 4 plus 6 is 10, or we can go via K, but 7 plus 4 is 11, so 10 is it there. Okay. Now let's consider the next set of vertices. Okay, so the vertices that are now reachable from H, K, E, and B. So we've got D and we've got C. Okay, so 9 plus 7, okay, that's 16 hours. Or we can go to C via E. Okay, 8 plus 4 is 12. So we put the lower of the two numbers, or the two values that we've worked out. Okay, and to get to vertex D, okay, we can either get to vertex D from E, so we can go E to D, so 8 plus 8 is 16, or we can go to vertex D from H, 10 plus 5 is 15. Okay. Finally now, to get to vertex T, okay, so this is our destination vertex, we can go via C, so 12 plus 3 is 15, so it's 15 hours, or via D, 15 plus 9 is 19 hours. So clearly from C to T is the shorter, or the one that takes the least amount of time. So that's going to be 15. Okay, 15 hours. Now we need to work out the actual path. That was the path that results in the shortest amount of time taken. Okay. All right, so again, we're going to backtrack. So starting at S, we're going to end at T. If you can remember some of the edges that you've used, that will actually speed it up. But let's go through the process of backtracking. 15, okay, minus 3 gives you 12. 15 minus 4 will not give you 15. So it can't be this edge here. Okay, so the edge that's part of the shortest path is edge CT. Okay, so from C, again, we've got two paths back from C. we've got 12 minus 7, that gives us 5. Okay, but we got 9 here, so it can't be this edge. Or 12 minus 4 is 8, and we've got 8 here next to vertex E, so it's this edge here. Okay, now from E, okay, going back, 8 minus 3, well that doesn't work. Okay, so that's 5, we've got 9 there. 8 minus 8, well that's 0, we certainly don't have 0 there. Okay, 8 minus 7, well that doesn't work. Okay, because 8 minus 7 is 1 and we've got a 7 there. 8 minus 5 is 3 and we have a 3 there. So this is part of the path as well. Okay, and then finally 3 minus 3 is 0. Yep, and that works. So the shortest path is S. Okay, so now trace it through. SA, E, C, and T. Here is another example involving shortest paths. If you like, you can just pause the video and draw the diagram in your notes and give it a go. Okay, and see if you can come up with the shortest path using the algorithms that we've looked at. So I'm going to go through and do the work solution now. Okay, so if you've given it a go, compare your solution to what I'm going to do, and hopefully we'll get the shortest path that's going to give us the least weight. All right, let's start off with the vertices that are basically one hop away from the start, away from S. We've got A, C, and D. A is 7. Okay, D is 6. Now, C is 12, but it could also be 11. Okay, so we can go 7 plus 4 to give us 11. We can also go 6 plus 3, which is 9. Okay. All right, so now let's look at vertex, actually the vertex B, vertices B, T, and E, in fact. I was going to say just B and E, but T is also reachable now from C. Okay, so let's see what we have here. B is reachable from A, but it's also reachable from C as well. So 9 plus 5 is 14, 7 plus 10 is 17. So 14 would have to be the lower number, the lower of the two, obviously, and that's the one that we use in terms of the weight for vertex B. And E, well, E, there's only one way to get to E, which is via D. So 6 plus 10 is 16. Okay. And T can be reached from C. 9 plus 13 is 22. Okay, so I might just put the 22 there, but I think we're going to do better than that. Okay, so now let's have a look at T via B and via E. So T can also be reached from B. So 14 plus 6 is 20, so that's the lower of the two values. So I'm going to cross off the 22, and now it's now 20. 16 plus 8 is 24. Obviously, that's a lot higher than 20. So we've now found the shortest, we've found the weight of the shortest path, which is 20. Now let's actually find the shortest path. So by backtracking, okay, 20 minus 6 is 14. So I'm just going to draw this edge in there. 14 minus 10 is not 7, so it can't be that edge there. 14 minus 5 is 9, so we go down to C. Okay, 9 minus 3 is 6, oh that will work. 9 minus 4 is 5, well that won't work, so it can't be that. 9 minus 12 is a negative number, and that won't work either. So it's in fact down to D. Okay, and 6 minus 6 is 0, so that would be our critical, our shortest path. So therefore, the shortest path is S, D, C, B, T. Okay, with weight 20. In this video, we're going to discuss the basics of activity tables, and in particular, the use of activity tables to list activities that form part of a project. Okay, so this is one of the applications of networks that we could actually use the network to help manage a project from start to finish. We have activities here that have to be done in a certain order. What you'll notice is with an activity table, there's typically 3 columns. You list the activities. Okay, so each of these activities could mean something. So if we're talking about making a cup of coffee, which is a project, what are some of the things that are involved in making a cup of coffee? You know, we've got to fill the kettle with water. We've got to boil the kettle. You know, get the cup ready with the coffee and the sugar. You know, we pour the water and into the hot water into the cup. Add the milk, stir it, and then enjoy the coffee. Right. So that could be an example of a project. What we're going to focus on though is we're going to build or draw our weighted directed network, okay, based on the information given. So this is just some random table I came up with just for the purposes of this video. And you know, we talked about these 3 columns here. The first column is activities. Okay, the second column is called the predecessor column. Another way to think of the predecessor is what activities have to happen first before the activity in the first column can take place. So for example, activity C can only take place once activity A and activity B are completed. So another way we can think of the word predecessor, we could replace it with depends on. Okay, so C depends on A and B. D depends on C. E depends on A and D. F depends on E, and so on. And then the last column is a time column, a time cost. So each of these activities will take a certain amount of time. So it could be minutes, hours, days, weeks. It doesn't really matter. It's just indicative, whatever the time is, you know, whatever unit of time we use. So, okay. Now you notice at the first row, the predecessor is just a dash. That means that from the start, A and B are the starting activities. So the way we draw that, now hopefully I'll have enough room here. So I'm just going to draw just a starting vertex here. So we're going to call this the start. Okay. And another thing when we're drawing the network diagram is that it's edge based, not vertex based. The vertices only really indicate the start and end of an activity, but the activity itself is indicated by an edge. So let's draw in A and B. So we've got A and B. Okay, and we draw in an ending or an end vertex. So I'm going to write the activity or label the activity in red. And so that's activity A, and it takes 3 minutes or 3 units of time. This is activity B and needs 5 units of time. Okay, what I like to do as well is I like to just indicate that I've actually drawn in these activities in the diagram. So A and B, we've already covered those. Let's have a look at C. Okay, C depends on A and B. So I could draw C here, for example, between these 2 vertices. Okay. And C requires 2 units of time. But we have a bit of a problem. C also depends on A. Now, one of the rules with drawing a weighted directed network, and especially when it's to do with activity tables, we're not allowed to have multiple edges. So if you recall, remember multiple edges? So you could have 2 vertices and multiple ways of getting between these 2 vertices. I'm not allowed to have that at all. Okay, so that's one of the rules of this particular idea. It's sort of the drawing the network diagram based on an activity table. No multiple edges. We need to introduce something though to help us though in this case. How do I join A and B together without creating a multiple edge? We use what we call a dummy activity. Okay. A dummy activity doesn't do anything at all. In fact, it's got a weight of 0. So we don't add this in terms of its weighting, or doesn't contribute any extra time or anything like that. So that all this means is that C depends on both A and B. That's all that dotted line is there to indicate. That's it. Okay. All right. So C is done. So we can put a little dot there to say we've done that. D depends on C. So that's fine. So I might just put D between these two there. Okay, so D depends on C, so that's D, and 6, it needs 6 units of time. Right, now E depends on both A and D, so A and D. So I might just put E here somewhere. Okay. I'm just sort of running out of space. Usually I go from left to right as much as possible, but in this case, sort of limited for space here. So we've got, this is activity E. E depends on A and D. Okay. So, but A has to join up here as well. Okay. So since you've got two vertices here that are predecessors, okay, so E depends on both of those. Look, I would probably advise that you draw your diagram in pencil. It's possible to probably rub out an edge and redraw it somewhere else. But if need be, you can introduce another dummy activity. Okay, doesn't make it incorrect. It just means that the diagram possibly has more dummy activities than are actually required, than the minimum required. So I'm going to join A to this vertex here. Okay, so there's another dummy activity there. Sorry, it should actually be a dotted line. Okay, so there's my eraser there. Okay, so there's another dummy activity. So E now is drawn correctly, and it depends on both A and D being completed. So I can put a dot there to say, yep, all done. Now we've got two more vertices. So we've got F. F depends on E. Okay. But then looking forward, because I'm running out of space here, G depends on both C and F. So C and F, and then G is really our end vertex, our end activity. The vertex that's at the end of G is the end. Okay, so maybe what I might do is I might draw F here. Okay, probably in hindsight I should have probably drawn E maybe down, but that's okay. In fact, what I might do is I might just put that E there. Yep, I think that's a little bit better. All right, sorry that the diagram's a little bit okay, just not my ideal diagram, but anyway, so just have to make use of the available space on this little whiteboard. So this is activity F. Okay, and that costs 1 unit of time. All right. Now the final one here is activity G, which depends on both C and F. Okay. So there's maybe I might just draw this. So this is really our end vertex. Okay. And okay, so this is activity G, and this needs 4 units of time to complete. However, it also depends on activity C as well. So I could put in a dummy activity. Sorry, drew it wrong there. That should have been probably thinking, you made a mistake. That's all right, just testing. Okay, I might just fix that diagram. See why pencil's so important? Okay, well, I'm using a whiteboard marker, so I'm going to draw a dummy activity there. Okay, hopefully you can see that. And that will be our completed network diagram. So let's just quickly trace over it. F depends on E. Okay, so I think that's correct there. Yep. And takes 1 unit of time. G depends on both C and F. So I could draw G after F, okay, but C also is needed. Okay, in other words, we cannot complete G unless C's, we can't start G really unless C is completed. So I drew in a dotted line, a dummy activity from C to the start of G, and this basically represents what's in the last row of this table. Okay, hope that all makes sense. I know it might sound a little bit complicated with all these dummy activities everywhere, but really it's just honestly just follow the table 1 row at a time, and put in the dummy activities where need be. You try and avoid them where you can though. So if it's possible that two vertices can sort of come together, not create a multiple edge. As long as there's no multiple edges, then you can join 2 activities at 1 vertex. That's not an issue, provided you don't have a multiple edge. Okay, sorry I've stressed that a few times, but very, very important. Okay, thank you for watching and wishing you all the best. We're going to convert this activity table into a directed network. So it's just a simple table. It's just really to demonstrate, again, just another example of converting a table into a network. Okay. So in the first column, we have activities. Okay. And in the second column, we have the predecessors. Now I've just written in blue up here, and you might want to get into the habit of this. The word predecessor really just means depends on. So B, for example, activity B depends on A. Activity C also depends on A. Activity D depends on C, and so on. Okay, activity A doesn't depend on anything. So we're going to start off with just a starting vertex. Okay, so we'll just draw a vertex there with the word start on top. Okay, and what I'm going to do is I'm going to draw activity A, and all the activities are represented using edges, of course. Okay, and the start and finish of each edge, make sure there's a vertex at each end. Okay. So I just like to put a little dot as well to say that I've now used that activity, or I've represented that activity in the diagram. Activity B and C both depend on A. Okay, so I'm just going to branch off activity A with activity B and C. Okay, again, I recommend do this in pencil. Okay, so chances are you may have to change the diagram midway through, and then you can use pen later on to just to basically pen it in, and that's your sort of your final network diagram. Okay, so I've used B and C. Now D depends on C. Okay, but E depends on B and D. Okay, so in other words, B somehow has to join up with D. Okay, so the end of B and the end of D have to join up. So you could draw a whole new diagram, or you could alter this diagram, and this is why, again, drawing your diagram in pencil is so important. So what I'm going to do, rather than drawing D across, I'm going to draw D straight up. Okay, that's fine, it's permissible, that's still a valid network diagram. Okay, now B and D, okay, join up at basically one vertex. From this vertex, so where B and D basically join together, we can draw in activity E. Okay, maybe we can go this way. Okay, so I've used up activity E, and then finally activity F depends on activity E. So, and that's the finish. And there's our network diagram. Let's have a look at example 2, which involves converting an activity table into a directed network diagram. This is similar to example 1. All I've done is I've changed some of the predecessors to see what effect it would have on the network diagram. So if you've looked at example 1 already, it'd be good to compare example 2 now to example 1. So let's start. Activities A and B do not have any predecessors. So why don't we start off with our starting vertex and draw in our two activities, A and B. Okay, so they're done. Now, activities C and D depend on A and B being completed. Okay, so what you'll notice is that in the predecessor column, if you have two vertices listed in the one row, it means that they somehow have to join together. Now, we can't have A joining onto B directly, because that would create a multiple edge. We're not allowed to do that. Okay, remember, we can't have this sort of situation where you have two vertices basically connected via multiple edges. Okay, so that's not allowed. So what we're going to do is we're going to use a dummy, okay, a dummy activity connecting A with B. Now that A is joined back onto B, we can now draw in activities C and D. Okay. Okay, so there's activities C and D. Okay, branching off A and B. Now E depends on D, but F depends on C and E. Okay, so what I'm going to do is I'm going to draw activity E joining on to activity C. Okay, this way. So this is activity E. Okay, so if you're not convinced, okay, so B, okay, so A and B join here at this vertex. From this vertex here, it branches off to activities C and D, which is correct here. E comes off D, so at the end of D, we draw in E. Now F cannot continue unless C and E are complete. So in other words, when C reaches this vertex and E reaches this vertex, then we can start activity F. So there's our activity F there, and this is the finish. And this is the network diagram for activity 2. Hi everyone, time for another activities table video. Now what I want you to do is, if you want to pause the video at some point soon, here's an activity table, alright, sort of activities, some predecessors. See if you can come up with the network diagram for this. Okay, so if you want, pause the video now. I'm assuming by now you've unpaused the video and you now want to have a look at the work solution. So your diagram may look a little bit different to what I'm about to draw. So let's start, shall we? Activity A, no predecessor. Okay, so what we'll do first, and we'll start off with our starting vertex, right? A little dot there with the word start, of course. A has no predecessor. Remember that activities are represented using edges. Okay, make sure that each activity has sort of a vertex at each end to kind of act as a start and end for each of the activities. Now, B and C both have activity A's predecessors. That tells you that when you have two activities with the same predecessor, it's like a branch, okay? It's going to branch off. So it should look something like this. There's B, there's C, all right. Little vertices there at the end, okay? So I think we're all good there, okay? So I think we've done that, done that. Okay, now D depends on B, E depends on C. Now F depends on D and E. Notice, sometimes it helps to just look forward a little bit. Go down the table and just see if you can notice, especially when there's pairs of vertices. So, or certain, sort of vertex pairs. DE sort of happens twice. We also notice that D depends on B, okay? E depends on C. So looks like that D and E have to sort of join together somewhere, right, at a vertex. So why don't we do that then? So, okay, D depends on B. All right, so let's put D there. E depends on C. All right, so far so good. Yep. Now, we've got activities F and G, okay, both depending on D and E, and then that's it. They're sort of like the end vertices or the end activities before we get to the end vertex. Okay, so let's draw activity F. Okay, so activity F is drawn at the end of end of activities D and E. So there's F, but also G is also an activity that depends on D and E. Okay. Okay. Now we have a bit of a problem here. We can only have one end vertex. Okay. What do we do? Okay. G is also one of the activities that we do at the very end. So they all have to end at a vertex, at the ending vertex. So you're probably thinking, hopefully you're saying, dummy activity. Well, we can do just that. Okay. So that means then that F is our sort of our terminal or terminating activity. G is also a terminating activity, but it needs to terminate kind of like at the last station there. Okay, sort of the terminating station, which is our end vertex. Okay, hopefully your solution looks like that, and wishing you all the very best for your studies. Here is another example that looks at converting an activity table into a directed network diagram, and somewhat like examples 1, 2, and 3. This one's a little bit different though, in that some of the activities, if you notice, have 3 predecessors. So we've got activity D has 3 predecessors A, B, and C. Activity G has predecessors E, D, and F. H has 2 predecessors. Notice also that I depends on D alone. Okay, whereby, say for example, activity G depends on both E, D, and F. Now, there's certain things here that are going on that we have not seen in the other examples. So let's start this one. Now, again, I recommend that you draw these directed network diagrams in pencil first, because chances are, look, you're probably going to make a mistake somewhere, or you may have to redraw the diagram to accommodate, some I guess some connection or some sort of a relationship that you can see here between an activity and its predecessor. All right, so let's begin. We'll draw our starting vertex. Okay. You notice also that A, B, and C do not have predecessors. So let's start with those. Okay. Right. Now we have activity D depends on A, B, and C. So again, to avoid our multiple edges, okay, we'll draw in our dummy activities, okay, and then we can draw activity D. Okay, now something here we just got to be very careful about. Okay, activity G depends on E, D, and F. Yet activity I just depends on D alone. Okay, so what I'm going to do is I'm going to actually I've just done D there. What I'm going to do is I'm just going to draw activity I after activity D. Okay, so I might just draw activity I this way. Okay, so that's done. Now activity E is drawn from activity A, as in drawn from the end of activity A. And activity F is drawn from at the end of activity C. But activity G is drawn from the end of E, D, and F. Okay, so E and F are included here. So in other words, we can draw E and F this way. Okay, E depends on A. Okay, F depends on C. But we have a bit of a problem in doing so. What's the problem here? Looking at this diagram, it looks like activity I depends on E, D, and F, but I only depends on D. So what do we do in this case? Okay, have a think about that. I'm going to rub out this diagram, or at least part of this diagram, and I'm going to redraw it now so that it accurately represents what's in the table. Okay, how do we ensure that the way this network diagram is interpreted correctly? Okay, that I only depends on D. Okay, so what I'm going to do is I'm going to draw activity D again. This time round, what I'm going to do is I'm going to add a dummy activity here. Okay, and I'm going to draw activity E. Okay, so that's that one there. And I'm going to draw activity F, joining together here at this vertex, which is drawn at the end of a dummy activity that's drawn after D. Now I can draw in activity I. Okay, so now activity I comes off activity D exclusively. Okay, E and F and D via this dummy activity, okay, end up at this vertex here. Okay, so I can now what I can do is I can now draw in activity G. Activity G depends on E, D, and F. Okay, so that's G. Okay, now H depends on A and G. Okay, so there's A here. Okay, and there's activity H. Okay, but activity H also depends on A. Okay, so the way I'm going to basically show that is again through a dummy activity. Okay, that way. Okay, so that's H. Now finally, H is one of the, it's a terminating activity. In other words, it's an activity that occurs just before the end. But so is I for that matter. So we're going to need one more dummy activity. This way. Okay, so just be careful when you're drawing these network diagrams that it's very important that you do show the dummy activities and in fact all the activities correctly and without any ambiguity, okay, or any sort of lack of clarity. It's important that it's very clear that anyone looking at this diagram can clearly see that there is a, you know, what the connections are, where the dummy activities are. In this activity tables example, we're going to do this example basically back to front compared to the other examples. Okay, so with the other examples 1 to 4, we've started with an activity table and we converted that activity table into a network diagram. This time around, I'm giving you a network diagram and I'm asking you now to come up with the activity table, okay, that describes this network diagram. If you like, you can pause the video now, give it a go if you like, and then unpause the video and check your solution against mine. Okay. What I'm going to do though, considering that probably don't have enough space under the diagram here, I'm going to draw the network table, or the activity table, sorry, just on this board here. Okay, so activity, and this is the predecessors just here. Okay, I've just abbreviated them just to save some space. You should write the full words obviously in your solution. Okay, first of all, just analysing the network diagram. We have 1, 2, 3, 4, 5, 6, 7, 8, 9 activities, okay, from A to I. So what I'm going to do is I'm going to list the activities first: A, B, C, D, E, F, G, H, and I. Okay, might just draw this across. Obviously, if you have a lined or a ruled exercise book or a grid book, it obviously makes things a little bit easier, of course. Okay, now next thing, let's have a look at the predecessors. Okay, and you don't have to fill this out in order necessarily. You don't have to go from A to I. You can just look at the diagram and sort of fill in what are some of the more obvious ones. So I think the obvious ones to begin with are the activities that don't have a predecessor. So A and B, okay, come from the start. So there's no predecessors for A and B. Okay. Now another easy one is probably activity D, which just depends on activity B. Okay, so activity D has activity B as a predecessor. Okay, activity C, okay, is drawn from this vertex here, and that depends on both A and B via this dummy activity to be completed before activity C can start. Okay, what about activity E? Okay, activity E depends on both activity B and activity C. So what you should be looking at is the edges, or the basically like kind of like an inflow, or sort of an input to that vertex. So the two inputs to this vertex here at the start of activity E is activity C and also activity B via this dummy activity here. Okay, so E, okay, would have B and C as predecessors. F's fairly straightforward. F only has D as a predecessor. Okay, so G and H, okay, both have identical predecessors. G and H both have E and F as predecessors. Okay, and finally, activity I has activity H as a predecessor, and that's our activity table, okay, which describes our directed network diagram that was seen earlier. In this video, we're going to look at a fairly simple example to do with forward scanning in networks. Okay, so if you want to just give this a go as a bit of revision, you're welcome to pause the video at this point and just see if you can fill it out. Don't worry about the backward scanning part just yet. We're only worrying about forward scanning for the time being, just as a little bit of practice. Okay. Now, we're going to go through the solution now. Okay, so the top boxes are what we're going to fill out. Okay, the bottom boxes are used for backward scanning to work out the latest or the latest start times for all the activities. The top boxes are used to work out the earliest start times. Okay, so let's go through this together. Okay, so the start, it always starts off at 0. Okay, because it's like that's sort of the start of time. Okay, or the start of when the project, or the start of the project. Okay, for whatever time it starts. Okay. Now, activity A takes 1 unit of time, and there's no other way to get to A, so this box here will have a 1 in it. Okay. Now, this box here, there's two ways to get to this vertex here. Okay, we can either go via B, okay, or via E. Now, if we go via B, okay, B takes 2 units of time. We're already used up 1 unit of time, so that'll take 3 units of time. Okay, so I might just do some working out here. Or we could go via E, okay, to get to this vertex here. But E takes 5 units of time. Now, it's the higher of the two numbers, okay? So we have 3 or 5, we put the higher of the two numbers. And the reason for that is because E takes a longer amount of time, okay? In other words, we can't start activity F or activity C unless activities A, B, and E are complete. Now, while E is getting completed, A and B are also occurring at the same time as well. But A and B don't take as much time as activity E. But we can't do anything past this point here unless activity E is finished, okay? So that's the rationale behind that, all right? Okay, moving on then. We have activity C, which takes 3 units of time, and we're already sort of at the 5 unit mark, or the 5 time unit mark. 5 plus 3 is 8, okay? Now, getting to the end, okay, we can get to the end via F. Obviously, to get to the end vertex, we have to complete activity D and activity F, in fact. So there's 2 ways then to get to the end, or there's 2 activities that have to be completed in order for the project to be completed. Okay, we got activity F takes 6 units of time. We're already at the 5 unit mark here. Okay, so 5 plus 6, that's 11, okay. The other activity that has to be completed, okay, is activity D. We're already at the 8 time units, or 8 units of time mark there, hours, days, I don't know, whatever we're measuring it in. We're at 8 here, okay, adding 4, we get 12, okay, we pick the higher of the two numbers, okay. So what this is saying, this 12, it's saying that this project is going to take 12, at least 12, we can't do it in under 12 units of time. So whatever unit of time we're using, whether we're using hours, days, weeks, years, 12 is the minimum. Here's another example on forward scanning with networks. What I'll invite you to do is to pause the video at some point, maybe copy down the diagram or just briefly sketch the diagram and have a go at filling in the boxes on top. Okay, so the ones on the bottom, again, we'll just leave them aside for now. I'll do a separate video with the backward scanning and the float times, but just fill in the top boxes for now, okay? I'm gonna fill them in a few seconds, so if you wanna pause the video, pause it now, okay? All right, I'm assuming you've unpaused the video, so let's fill in the boxes, okay, and work out the earliest start times, okay, of the activities. So the start is always 0, okay, so that's the start of the project. Okay, activity A takes 5 units of time, okay, and there's really no other way to get to A, so 5 goes here. Okay, activity B takes 2 units of time, okay, but we can't start activity C unless activity B and activity A have been completed. Now, activity A takes 5 units of time, takes longer than B, in fact. So which number do we put in the top box here? Either 2 or we put the 5, okay? We take the higher of the two values, so we're going to put 5 there. And the reason why, again, we cannot start activity C unless activity B is finished and activity A, and A takes longer. So C is just going to have to say, be put on hold and go, well, okay, I can't do anything unless A is done first, okay, unless A is completed, and obviously B is completed, but B takes less time, so B can be just hanging around as well, going, well, okay, I'm done, floating around, and that's where the float time comes in, so B can sort of move, can be started a bit later or earlier, but we'll worry about that later. Okay, moving on, activity C. Okay, it takes 3 units of time, and we've already used up 5 here. Okay, so 5 plus 3 is 8, so we have a choice. Or we can get to the end of activity C with that vertex also via activity D as well. So D takes 7 units of time, we've already used up 5, so we have a choice of 8 or 12. So we take the higher of the two numbers again. And again, the reason for that is we cannot begin activity E or activity F unless both activity C and activity D are complete. Okay, so we can't move on. So that's always got to ask yourself that question. We cannot move on, okay, beyond this point unless the activities before that point are complete. Okay, every one of them has to be complete. Okay, so kind of like a relay of passing battens. You know, D has to pass the baton on to E, right? C also has to pass the baton on to E, but C's done earlier. D takes a lot longer, so E has to just hang around and just wait and go, well, I can't move anywhere until D sort of hands the baton across. So, okay, so let's get rid of that there. All right, moving on. We have one way to get through activity E to this vertex here, and that takes 6 units of time. We already used up 12, so that'll be 18. Okay, this box up here, that occurs after activity F. Now F takes 1 unit of time. Okay, so 1 plus 12 is 13, but we can't start activity G unless both activity F and activity E are completed. Okay, so, well, 12 plus 1 is 13. Okay, but we also have, you know, an 18 here via this dummy activity. Remember, dummy activities are only worth 0. So it doesn't do anything, right? I mean, it's just a way of connecting the end of activity E to the start of activity G. So we have 18 there. Okay, well, okay, so obviously the 18 is the larger number. So we're almost at the end now, actually. So now to get to the end of the project, or the project finish, both activity G has to be complete and activity H has to be complete. Okay, so we have 18 plus 4, which is 22. Okay, or 18 plus 8, which is 26. Okay, so in other words, we can't get to the end and say, well, project's done and dusted and all over unless both G and H are completed. Okay, so G's completed pretty early, and it takes 4 hours. H takes a lot longer, so we can't say and say officially project over until H is done. So 18 plus 8 is 26, takes the longer amount of time. That's what goes in the top box. We're going to determine the latest starting time for each of these activities in this particular example. Just to save a bit of time, I've already done the forward scanning, so you may want to maybe check this for yourself to make sure I've done this correctly. But if you recall with forward scanning, if there's multiple ways of getting to a vertex, we need to basically enter in the number in the domino, in the top box of the domino, which is the higher of the two numbers, or the higher of the two paths, or whichever one takes the longest amount of time to get to that vertex. Okay, so assuming that is correct, I've checked it, hopefully it is correct. If you notice any errors, please get in contact with me. Otherwise, let's work out now the latest starting time for each of these activities by backward scanning. Okay, so forward scanning, okay, however way you would do that, with backward scanning, it is exactly the other way around. In fact, with forward scanning, when we're adding numbers to get to the finish, with backward scanning, we're actually subtracting the numbers, okay, or subtracting the times in order then to get back to the start. Okay, in doing so, we can then determine which of these activities is in fact what we call a critical activity, that is an activity that cannot be delayed, or an activity that does have a little bit of leeway, an activity that could in fact be delayed by whatever many minutes we can determine, or what we determine. Now, backward scanning, we start off with the bottom box, which is 29. So let's assume it's minutes in this particular example. So starting off with 29 minutes. Now, if there's only, going backwards, if there's only one way to get to the next vertex, then just subtract the number or the time that's associated with that activity. So 29 minus 10 will be 19 in this particular instance here. Okay, so now you might immediately notice that the difference between the top box and the bottom box of this domino is 9 minutes. So that means that we do have some float time. That actually means then that the activity, in fact activity B, could in fact be delayed. Okay, so by up to 9 minutes. Okay, let's go to fill in, or let's fill in the rest of these dominoes. So 29 minus 6 is 23. Notice that these two numbers are identical. that means that activity F cannot be delayed. Okay, we have no choice. We have to start activity F on time. Okay, now going back through activity H, so 23 minus 9 is 14. Again, top box and bottom box are identical, so therefore activity H is a critical activity. We don't have any delay. We can't delay activity H, or else the whole project will be late or will be delayed. And going through going through activity G, or back through activity G, 14 minus 5 is 9. Or we can get to this vertex via activity E. 23 minus 8 is 15. Well, obviously, 15 is much bigger than 9. We put the smaller of the two numbers. Okay, so just like with forward scanning, you put the larger number if there's two ways or multiple ways of getting to a vertex. With backward scanning, the smaller of the two numbers then goes in the bottom box. Okay, so everything's just the opposite, okay, of forward scanning. Okay, so however way you were taught to remember forward scanning, or whichever way you know how to do forward scanning, just think it's the exact opposite thing. Okay, moving now to this vertex here, so the vertex between A and D. We can either go through one path is through activity D. 9 minus 3 is 6. Okay, I'm going to put that because you can't get a number that's smaller than 6. The smallest it can be is 6. You can't get 5 there, because then you'd get a very strange float time of -1, which kind of doesn't make sense in this context. The other option, or the other way to get to this vertex here, is via activity B. So 19 minus 4, again, that gives you 15. 15 versus 6, well, 6 is the smaller number, we put the smaller number here. And now, to get back to the start, well, there's only one way to get to the start, which is through activity A. 6 minus 6 is 0. The start will always be 0 anyway. So how do we interpret these later starting times? The later starting time of activity A is 0. There's no delay, okay? Because the difference between the top and the bottom is 0. The later starting time then for activity D is in fact 6, or 6 minutes past the starting time, or whatever the starting time is. Because with activity B, after activity B, we've identified that we do have some float time here. That means then that activity B could in fact be delayed. Okay, and we've actually determined this with backward scanning, that some of these activities are critical activities. In other words, there's no delay. So D cannot be delayed, G cannot be delayed, H cannot be delayed, and F cannot be delayed. In fact, I might actually just maybe highlight this particular path. This path here, this path here, this path here, this path here, and this path here. So altogether, these particular paths make up what we call the critical path. This blue line represents the set of activities, or the sequence of activities, that has 0 float time. In other words, where there is absolutely no leeway whatsoever with these activities. Okay, B and C are not critical activities. Because of the float time here that we've just determined, we can delay B and C. Now let's have a look at an example that involves backward scanning. Okay, so this is the same network that we did the forward scanning example on before, and I've left the values in the top boxes in there. So with forward scanning, if you recall, forward scanning works out the earliest start time, the EST. Okay, if you remember what that was. If you don't know what that is, that basically means what is the earliest I can start an activity without it really impacting the project. Okay, so for an example, let's say for example, activity A starts at midnight. I can start activity B, okay, at 1 AM. I can't start it any earlier than 1 AM. Activity E starting at midnight, okay, for example, gets to this vertex here, but activity F and activity C cannot start any earlier than say 5 AM. Okay, so again, sometimes I like to use actual time of day to help understand this idea of earliest start time. So now let's have a look at latest start time. We can see that, for example, activity B could be started a little bit later. We do have a little bit of leeway there, but we may not have any leeway anywhere else. So how are we going to do this? Okay, we're going to use the bottom boxes, and we're going to start off at the 12-hour mark. Okay, or basically the end box should look identical top and bottom. Okay, the 12 and the 12, obviously, I mean, we're starting from 12 and going to go backwards. We're going to end up at 0. Okay, so the start box and the end box should look, the top and bottom boxes should be identical to each other. We're going to do the same thing now as forward scanning, except we're just going to do everything in reverse. Okay, instead of adding numbers, we're going to subtract numbers. Instead of putting in the number that's highest in a box, we're going to put the number that's lowest. Okay, so everything is basically flipped. It's back to front. Everything is just the opposite of what we did with forward scanning. All right, so let's begin. 12, okay, minus 4, there's really only one way to get to this vertex here. So starting with the blue numbers now, 12 minus 4 is 8. Okay, we can see that activity D, there's no leeway there. Okay, we start at 8, we can't do it we can't start activity D any later. Okay, we start the earliest and latest, in fact, identical to each other. Now, there's two ways we can get to this vertex here. This is above the 5, okay? So 12, going through activity F, 12 minus 6, okay, is 6. We've also got 8 minus 3 is 5. We put the lower of the two numbers this time instead of the higher, okay? So we put 5 there, all right? Okay, so far, again, we've shown that there's no leeway, okay, or float time, basically, for any of these activities. Let's now go through activity B now. So, again, we're using the blue numbers. 5 minus 2, okay, that gives us 3. Okay, notice now with activity B, the top number and the bottom number is different now. That means that we do have a little bit of leeway with activity B. Starting activity A, we can wait up to 2 hours. This is what this is saying, before we start activity B, and it will not delay activity C or F, okay? And it won't even delay the project in its entirety, okay? Now, going now to the start, okay? The blue number has to be a 0. Now, just to show you why, again, 3 minus 1, okay, gets us back to the start. So going through activity A, 3 minus 1 is 2. We've also have this number here from this vertex going through activity E. 5 minus 5, okay, is 0. Okay, again, we choose the lower of the two. It's going to be 0. Okay, and that's how we do backward scanning. Okay, so we call this backward scanning. Actually, we use backward scanning to work out something called LST, which is latest start time versus earliest start time when we're doing forward scanning. Let's have a look at another example now involving backward scanning to calculate the latest start times of each of the activities. So I'm using the same example that I used for the forward scanning activity that we had done previously. And I've left the numbers in red here, which are the earliest start times of all the activities. Okay, so now with backward scanning, again, backward scanning, we just do the exact opposite of forward scanning. Instead of going with the flow of the arrow, we go against the flow of the arrow. Instead of adding numbers or adding the weights to the cumulative total, we're going to be subtracting the weights. Because everything's back to front. The whole thing's just the opposite of forward scanning. Whatever you do with forward scanning, it's backwards. The other thing we need to bear in mind is that we also plug, if there's two ways to get to a vertex, we put the lower of the two numbers or whatever the total is in the box instead of the higher of the two numbers or the 3 or whatever. Okay, if there's multiple paths to a vertex. Okay, so going through now activity G, we're going to start off, the bottom number now starts off with 26, so it should always match the number on the top. 26 minus 4, okay, gives you 22. Okay, there's only really one way to go back through activity G to this vertex here. Okay, now to this vertex here, okay, we've got 26 minus 8 is 18. Okay, or we can go through this dummy activity, 22 minus 0. Remember, dummy activity is only worth 0. So 22 minus 0 is 22. Okay, so well, pretty obvious. Put the lower of the two numbers, so this will be 18. Okay, all right. Now, going to the vertex that's before activities E and F. Okay, we got 18 minus 6 is 12, or we've got 22 minus 1 is 21. Okay, so we put the lower of the two numbers again, so we put a 12 there. Okay. Okay. So now going back through activity D and also through activity C, we can do activity D first. So 12 again, we use the numbers in blue. 12 minus 7 gives you 5. Okay. 12 minus 3, so going back through activity C, 12 minus 3 is 9. Okay. Now, going back through the dummy activity, 9 minus 0, well, that's obviously 9. It's higher than 5, so we'll leave the 5 where it is up there. Okay, it's always the lower of the 2 or 3 numbers, or whichever way you calculate to get to a particular vertex. Okay. Finally, now to get to the start, we can go through activity B. So 9 minus 2 is 7, or 5 minus 5 is 0. So again, the lower of the 2 numbers, we put a 0 there. And obviously it's going to be 0 because, well, that's where the project starts. Okay, so when you're starting backward scanning, probably the easiest 2 boxes to fill out, or the easiest 2 sets of boxes to fill out, are the ends. Okay, so the top and bottom should match, and with the start, it starts at 0, should end at 0 as well. Okay, now notice that some of the sets of boxes will have a different number top and bottom. The number in red is different from the number in blue. So for example, activity C could be delayed by up to 4 units or 4 hours of time. Let's say we start at midnight, we start activity C, we can't start any earlier than 5, but we can start it at 9, up to 9 a.m. without delaying the entirety of the project or the running time of the whole project. Same thing with activity G as well. Okay, activity G could be delayed up to 4 hours. Okay, and still not affect the end time of the project. Something else that's worth noting as well is that activity B here. Okay, that's only 2 hours. We could actually start activity B a bit later, even though the box before activity B shows 0, 0, which seems to indicate that there's no float time or there's no leeway with activity B. There actually is. In fact, if you take the 2 red number, or the basic numbers in red, on either side of the activity, you start, so for example, activity B, 5 minus 2, okay, gives you 3. That means that the float time for activity B is in fact 3 hours. Now, activity C, for example, takes 3 hours. If you take the numbers in red, 12 minus 3 minus 5, okay, gives you 4. That gives you the float time, okay, of activity C. Same thing with, say, activity G. 26 minus 4 minus 18, okay, gives you 4. Okay, so again, that's the float time for activity G. Okay, and so on. That's the same basic idea. We'll look at this in a bit more detail in another video where we do calculate some float times and which activities, in fact, could be delayed. But that's the basics of backward scanning. Let's have a look at float time in directed networks. And I'm going to use as an example the coffee example that I had used earlier. But this time what I've done is I've just simplified it into a very basic 3 activity project, which involves boiling the kettle, which takes 5 minutes. We've added an activity here, which is add coffee, which takes 1 minute, and another activity here, which is adding the sugar, which also takes a minute as well. Now, I've already done the forward scanning and filled in the dominoes, the top box of each of the dominoes. So 0, adding 1, you get 1, 1, adding 1, you get 2, or you can go from the starting vertex to the ending vertex via this activity, boiling the kettle, which is 5. So obviously you've got to pick the larger number, which means that our project, if it was to say starting at 10 o'clock, and it does help, I think sometimes if you want to think of an actual start time, I just make up an arbitrary one, 10 a.m. Okay, the project's going to finish at 10:05. So I know there's other parts of making a coffee, of course, but I've just for the sake of explanation, I've just focusing on just these 3 basic activities. Now, it's fairly obvious then that if the kettle's going to take 5 minutes to boil, adding the coffee to the cup does not have to be done at 10 a.m. I could add the coffee at 10:02 or even 10:03. In fact, how late could I add the coffee to the cup without delaying the project? So clearly I can't add the coffee at 10:05 because then that would delay the project by a minute. I'd be drinking the coffee at 10:06. So we need to work out then how late could an activity be started without impacting the end time or the actual total time of the project. Okay, so in this case here, we want to try and work out, well, how late could I add the coffee without affecting the end time? So what we're going to do is we're going to do something called backward scanning. And that's where the bottom box of each of the dominoes comes into play. So starting now with the end, right? The end's 5 minutes, and now we're going to backtrack. Okay, it's a bit like equations, I guess, when you're sort of doing the inverse or the opposite operation. If forward scanning, you're adding numbers. Backward scanning, you're subtracting numbers. Okay, so it's almost the same thing, just sort of in reverse. So starting with 5 minutes, let's go up sort of this path here. So 5 minus 1 is 4. Okay, now we have two options then. Now to get to the starting vertex, we can either go from the end vertex to the start directly via this boil the kettle, or we can go via this vertex here via the adding coffee activity to the starting vertex. 4 minus 1 gives you 3. 5 minus 5 gives you 0. Now, because it's the starting vertex, this has to be a 0 anyway, but it's good for you to see that we actually got to take the lower of the two numbers anyway. So the 0 goes here at the starting vertex regardless. Okay. In more complicated diagrams, that's a very important point. If there's multiple ways of going backwards to a particular vertex, you enter in, or you put in you write in the lowest number. Okay. Opposite to forward scanning, you put in the higher number. Backward scanning, you put in the lower number. Now we'll get to this float time. So float time, it's a bit like, I guess leeway is probably another way to think of it, or slack time. That really tells you, well, how late could I, or how late could I start an activity without impacting the total time of the project. So by working out the difference between the bottom box of the domino and the top box, that gives you the float time. So in this case here, and then we'll talk about what this is. So float time here is 3 minutes. Okay. So what this means is that I could add the coffee 3 minutes after I start boiling the kettle, because adding the coffee takes a minute, adding the sugar then takes another minute, and that takes you then to 5 minutes. So the float time really tells you how much room or how much can I delay an activity without it impacting the project. Now, if I'm going to fill in the actual start time and end times using the times that I've used here. So at 10 a.m., okay, I've started boiling the kettle. It's going to end at 10:05. Now, adding the coffee, I could either start that at 10 a.m., okay. The sugar, the latest I can add the sugar is in fact 10:04. Okay, which means that because the coffee takes a minute, the latest I can add the coffee would be 10:03. And that's where the float time is very important. Okay, so always remember, float time, slack time, leeway, it just means that for certain activities, okay, not all activities will have a float time of anything other than 0, but some activities will have a float time. That means that those particular activities could be delayed or put on hold for a certain amount of time, and it will not impact the end or the finish time of the entire project. Another way to help you understand float time is if I consider two activities. So let's say this is activity A. Okay, and let's say activity A starts at 10 a.m. just for argument's sake, and activity A finishes at 11 a.m. so it takes 1 hour, okay, or 60 minutes. So I might just do this in minutes. Okay, so 60 minutes. Let's say then we have an activity B. Okay, and activity B is a shorter activity. Okay, and it goes for 30 minutes. Okay, Now, activity B also starts at 10 a.m., but it finishes at 10:30. What about all this time here? Okay, this is really spare time, isn't it? Okay. Okay, so it's really spare time of 30 minutes. Now, does that mean then that activity B has to start at 10 a.m. or could we start activity B really at any time? So a way to think of then float, or why it's called float time, it's actually quite straightforward. Let's assume this pen represents activity B. Activity B effectively floats on activity A. In other words, the length of activity B is still 30 minutes, but where it starts, we have some leeway there. Okay, so we have some flexibility as to when it starts. The latest it can start though is obviously at 10:30. Okay, so that gives us still enough time to finish activity A such that the entire project finishes at 11 o'clock. If we start activity B a bit later than 10:30, then the activity B will overshoot activity A and we've actually delayed the project. Okay, so think of float or float time as the activities that are non-critical float on the activities that are critical, and the amount of float that we have, so the amount of distance that the activity can float, really is just the gap. So therefore, that's why the formula is latest start time minus the activity length minus the earlier start time, EST. Now, in the previous example, we used backward scanning to determine the latest start time of each of the activities. So what we're going to look at today is to determine the float times for all the non-critical activities. And we determine the non-critical activities by the vertices that show a different EST and versus the LST. So in this particular example, okay, if you recall, if you watched the last video, we've determined the critical path, okay, with the blue line. Now we need to determine the float time of the non-critical activities. And the non-critical activities are all the activities that basically don't sit on the blue line, okay? So we've got B, okay, we've got C, D, we've got F, okay, and we've got G. Yep, just squares that there at the bottom. Okay, now to determine the float time, really there's just one formula, okay? So let's have a look at B, for example. You take the LST of the activity after B, okay? So the LST here is 17 minus the activity time of B itself minus the EST, okay, of B's earliest start time. So I might just write the formula here. So we're going to go LST, okay, which is 17, minus the activity time of B, minus the EST of B. Okay, and that gives you 6. Okay, now let's see if you can work it out for activity C. Okay, we work it out exactly the same way. All right, we take the LST, okay, of the activity after C, so LST, what we call LST next. You might have seen this, right? LST next, okay. Subtract out the activity time of C, then subtract the EST of C. Okay, so 25, okay, minus 8, minus 11 equals 6. Okay, now for activity D, okay, same formula. 32, the LST minus the activity time, so 32 minus 7 minus 19 equals 6. Okay, for activity F, again, LST, okay, 18 minus 3 minus 9 equals 6. It's just coincidental that they're all happen to be the same float times, but it is worked out this way. And for activity G, okay, again, LST LST next. So the LST of activity H, in other words. So LST minus 5 minus EST of G, which is 12. Which is 6. In this example, we're going to identify the critical path. So I'm going to go and identify the critical path by doing forward scanning first. Then we do backward scanning, and then we identify the activities that have the same EST and the same LST. Now, just forgive me, this video is probably going to go a little bit longer than the sort of the 2 or 3 minute mark. So if you can be patient, just watch the whole video all the way through, because I'm going to do basically both procedures, forward and backward scanning, and also identifying the critical path all in the one video. So first thing we'll do is I'm going to draw in the dominoes. Okay, so try and draw them fairly large, but where possible. Okay. And as long as you can read the numbers easily. It's a little bit tricky sometimes on a whiteboard to do this, but just bear with me. Okay, I think that's all the dominoes drawn in there. Yep. Okay, so from the start we have 0. Okay, it's always starting off from 0, and it also ends with 0, of course, when we go and do the backward scanning. Oh, we need one more domino here. Okay, now activity A is the first activity, so that's going to be 5. And let's just use 5 minutes. Doesn't matter. I mean, hours, minutes. This activity doesn't specify the unit of time. So moving on. So from this vertex, it branches out into two paths. Okay. So activity B, 5 plus 6 is 11. Okay. So that's that. And then we've got activity E as well that branches off from activity A. 5 plus 4, we've got 9. Okay. Now I'm going to branch, just going to do some of the easier dominoes first, and then we'll worry about the vertices where two paths intersect and come together. So from activity E, we can go and complete activity I. So we've got 9 plus 4, that'll be 13. After activity I, we can do activity K. So 13 plus 5 is 18. Okay, now where the intersections are, I'm not going to do those yet. I'm going to do all fill in all the dominoes that are just sequential paths, singular paths. Okay, so after activity B, so we've got 11, we've spent 11 minutes there, 11 plus 8, so after completing activity C, we'll have 19 minutes there. Okay, so now at this point, the remaining 3 dominoes, so 1, 2, 3, are actually intersection points or vertices where two paths basically join or come together, and we have to pick or choose the largest or the lengthiest path, and whatever the lengthiest path is, we'll write the number there. Okay, so after activity F, okay, so from activity E, so we're up to 9 plus 3, that gives us 12, okay? And after activity B, now the dummy activity is worth 0, okay? So 11 plus 0 gives us 11, but 9 plus 3 gives us 12. So 12 is obviously the larger number, so we put 12 there, okay? Right, now moving on then to this vertex here, we can get to this vertex via L and also via G, but let's work out which one's the larger of the two. So 12 plus 5, that's 17. We got 18 plus 5, which is 23. So clearly 23 is the larger of the two. So we'll put 23 there as well. Okay, we've got one more domino, which is the finish domino, or the end one. So we've got 19 plus 7 is 26. 23 plus 9 is 32. So 32 being the largest of the two. So this project, whatever this project is, takes 32 minutes, okay, from start to finish. Okay, now we're going to do the backward scanning, okay, to determine what the basically what the latest start time, the LST, is of each of the activities. And then finally, we're going to identify which of these activities have basically no float time, no leeway. There's the critical activities that must start and end at a particular time. Okay, so going backwards, we're just going to reverse the procedure now. So 32 minus 7 is 25. Okay. And also, so 32 minus 9 is 23. Okay. Now, again, just be careful with any paths where that intersect. So going backwards, we can have intersection points as well. And you've got to take the lower of the two numbers instead of the higher. Okay, so going back now, so going this way, again, I'm going to fill out the easier dominoes first. So 23 minus 5 is 18. Okay, you're already starting to see that there are some activities that have the same EST and LST, and they will actually form the critical activities that form the critical path from start to finish. Okay, 18 minus 5 is 13. Okay, now we have this intersection point here, so we can fill out one more. So 23 minus 5 is 18. Yep, so just making sure, always make sure you check along the way as well. It's quite easy to make mistakes. So I think at this point though, now we have a branch. So 12 minus 3 is 9, but also 13 minus 4 is also 9. So that actually works out well for us. So that helps us to fill in this domino here, the bottom box of the domino. Now, 18 minus 0, okay, is 18. And we've also got 25 minus 8 is 17. So we put the lower of the two numbers, so we're going to put 17 here. Okay, hope that makes sense. So again, we treat the dummy activity as an activity. It's worth 0. 18 minus 0 is 18. 25 minus 8 is 17. We put the lower of the two numbers. Okay, now 17 minus 6 is 11. Okay, 9 minus 4 is 5. So again, we put the lower of the two numbers. And then 5 minus 5 is 0. Okay, so now we've completed the backward scanning, and sorry, that needs to have a 32 there. I forgot to put that in before. Now we've completed the backward scanning. Now let's see if we can identify which activities have the same EST and LST. So clearly, just look for the dominoes that have the basic identical boxes top and bottom. So that's one there. That's one. That's one. That's one there. So clearly these two are not. There's one here as well. Okay. So that's not, and obviously the finish, start and finish are always part of the critical path, of course. I'm just going to use a different color pen here. So I'm going to draw in the critical path now, and then I'll write it down what it is. So we've got that there, okay, through activity E, okay. Now through activity I, all the ones that I've starred, okay, so through activity I, through K, okay, through L, okay, and then finally straight to the finish, and that's our critical path. So therefore, critical path. And we just list the activities. So we have A, E, I, K, L, and H. Here is another example where we look at critical path analysis and activity float time. So here's an interesting network here. It's just a sort of a random directed network that represents a project of sorts, I guess. And now I've already done the forward scanning. Okay, so these are the numbers in black, and the backward scanning are the numbers in green. So you may want to check that for yourself. If you recall with forward scanning, we check basically with vertices where there's multiple ways of getting to a vertex, we need to put the highest number, okay, when you add up the weight of the edges that make up the path. So for example, to get to this vertex here, we can go via A and D, okay, we can go via B direct, or we can go via C and E. So C plus E, so that's 3 plus 5, okay, gives you 8, which is definitely the higher of the three possible ways of getting to this vertex. And likewise with backward scanning, so going back against the flow, the flow of the arrows there, if there's multiple ways of getting to a vertex, again, the lower of the three numbers is what we put here. And so these are the numbers in green. Okay, so for example, we got this entire project takes 53, let's say, hours. It takes 53 hours for this project. 53 minus 14 is 39. 53 minus 15 is 38. Okay, so notice these two numbers here are different. This is the earlier start EST and the LST. Okay, of the activity before it, but it can also mean that either of these two activities here could be delayed, in fact, depending on which one's delayed. So 26, that occurs because this one here, 39 minus 13 gives you 26, 38 minus 11 gives you 27, so 26 is the lower of the three numbers, okay, and so on. Now, to work out the critical path, okay, we look at the boxes, okay, where the top number and the bottom number are identical, okay, so obviously we have this vertex here is on the critical path. This one is on the critical path, so I'm just going to put a tick there. This one's on the critical path, okay, notice that it's different here. This one's on the critical path because top and bottom boxes are the same. In other words, there's no slack time, okay. This one's on the critical path as well, and also this vertex is on the critical path, and of course the start is on the critical path. So drawing in the critical path then, so where I've ticked the vertices, okay, we can just draw in the critical path, okay. So I'm just going to draw it in green, okay, so like that, and up to this vertex there, and down to this vertex here. So there's the critical path there. Now, to work out activity float time, there's two ways of working this out. So I've decided, look, while there's two formulas, there's like a shorter formula and a more extended formula. It's the extended formula is actually the better one, okay? And so let's say we work out the float time for activity P, for example, okay? The way we work this out is we look at the two vertices, okay, that are on either side of P. Okay, you take the LST, okay, of the vertex after P, we subtract the activity time and then subtract the EST. Okay, so I might just do a few vertices here. So float time of P, okay. We take the LST, okay, which is 53, minus the activity time, minus the EST, which is 37. Okay, so think of it as almost like a sort of bottom box activity time, top box going backwards. Okay, so 53 minus 15 minus 37, if you want to work that out, should be 1, of course, and it is 1, and that makes sense. Okay, so the float time of P is 1. What about, say, M? Okay, so I might just raise it up a little bit. Actually, I'll just see if I can get a bit more of that board into the video. So, yeah, might be a little bit easier like this, actually. Yeah, that's good. Okay, so what about, say, activity M? What would be the float time for that? So, again, activity M. Okay, so okay, float time for M. We take the LST, okay, after M. So that's 38 minus the activity time. So 38 minus the activity time for M is 11 minus the EST. Okay, so minus 11 minus 26. And float time for M is also 1. And that makes sense. Since this path, okay, MP, we have a float time of 1. That means M could be, in fact, delayed by 1 hour, or P could be delayed by 1 hour, but not both. So we need to be very careful here that if we delay M by 1 hour, then P can't be delayed. Okay, so really depends on when M starts as to when P can start. But if we start M immediately, then we have an hour. We can then start P. So P really depends on when M starts. Let's have a look at, say, another one. Let's say, for example, activity A. What would be the flight time for activity A? We take the LST. Okay, again, that's the latest start time for activity D. Okay, so the LST, though, which is at the end of A, minus the activity time. Okay, for A, which is 1, minus the EST, which is 0. So the earliest we could start A is actually right on the start of the project. So 4 minus 1 minus 0 is 3. Okay, so float time. Okay, I might just write that here. So float time for A, okay, is equal to the LST, 4, latest start time, minus the activity time, minus 0, and equals 3. Sorry, I had to sort of squeeze it up there in that top corner. And likewise for all the other activities, it can be worked out the same way. So just to sort of cut a long story short, and sorry that the video has actually gone this far. So just to summarize this, so if we have an activity, for example, okay, and there's some activity there, and okay, so let's call that the activity, for example, activity X, okay, and it takes, for example, a certain amount of time. So let's say it takes T hours, okay. We take, this is the LST here, okay, and this is the EST here. Okay, this is the LST of the activity that comes after activity X, okay. So the float time for X, okay, is given by the formula LST, okay. So this is the LST of the activity after X, okay. This LST here, this is why I've represented it diagrammatically, okay. This LST, okay, minus T minus the EST, okay. So that should be LST, actually that should be LST next, just to make sure I clarify that a little bit more, okay. We don't worry about this box here, we don't worry about this box here when we're working out the float time. In this video, we're going to look at the basics of network flow and looking at an application of directed networks to represent real-life situations such as traffic flow or electricity flow or flow of water, for example, through a system or a network of pipes. And some of the things that we're going to be looking at, actually, probably the main thing we're going to look at really is the flow capacity of a network. In other words, how much could this network carry from one point to another? Let's have a look at a basic application, which is traffic flow, for example. And what I've done is I've sort of represented I guess a fairly typical example of say 3 lanes merging into one, maybe due to some road work or some other obstruction. And then at another point on the road further down, the road then opens back up to 3 lanes in the same direction, indicated by the arrows. Now, where the traffic emanates from, or the start, we call it the source, and we label that with usually with a capital letter S. And where the traffic ends up, or sort of the destination, we call that the sink, and it's normally labeled with a capital letter T. We label the weight of each of the edges as well with the number, or we designate the weight of each edge, which is actually the capacity of each edge with the number. So for example, in this situation, the number 1, actually that's a number 1 here as well, the number 1s represent 1 car at a time, basically. So we've got 3 lanes, and each of these lanes can carry 1 car each, and it's going to merge into vertex A. This is called the inflow. Okay, so the inflow at A, okay, is in fact equal to 3. Okay, because each of these edges represents 1 car each. Add them together, we're getting 3 cars merging into one at vertex A. The outflow of A, however, is equal to 1. So, in fact, the maximum outflow of the vertex A has to be the lower of these two numbers. So outflow, the flow capacity, or the outflow of the vertex is in fact going to be 1. Okay, there's obviously an obstruction. So 3 cars cannot just merge in together at A. One will have to wait behind the other, obviously, to avoid an accident. Likewise, the total flow capacity, okay, of this entire network would be 1, because it's limited by this edge AB here. Okay, so the flow capacity, which when we talk about flow capacity, it's the entire network. We can see here from this very simple example that it's going to be 1 car. Let's have a look at another example now of network flow where we want to calculate the flow capacity of this network. So recall that the source is normally or usually labeled with the letter S, uppercase S, and the sink is labeled with an uppercase T. So starting from S, now the 100 could represent anything, and especially if there's no context given, it might help to think of it in terms of maybe say water flow. For example, this could be 100 litres per minute is the capacity of this edge, SA. The capacity of edge AB is 10 litres per minute, BC is 20 litres per minute, AD is 30 litres per minute, DC is 40, and CT is 100 litres per minute. That doesn't mean that that's actually what's flowing in the pipe. If you recall from the video where we looked at traffic, 3 lanes going into one, and then 1 lane. So if you recall this situation, and then the 3 lanes branching back out again, the total flow capacity is 1 because of this restriction. Okay, so we need to keep that in mind. So what we're going to do is going to calculate now the flow capacity of this entire network. Okay, now these are interesting numbers here, 10, 20, 30, 40. If you add those up, you get 100. But let's calculate the flow capacity, because you may find that it could actually be less than 100. So the first thing we're going to do is we're going to determine the 2 ways that we can get from S to T. So let's, from S to T. And we can go via S, A, B, C, T. Okay, and the other one is S, A, D, C, T. And what we're going to do is we're going to calculate the capacity of each of these paths. Okay, and then we're going to add those together, and that'll give us the total flow capacity. So from along this path, what we're going to look for is the smallest number, because that's the restriction. So the smallest number, or the most restrictive edge, is edge AB, in fact. So in fact, once you put 10 litres through S into A, and then diverting that to B, you've saturated, or you've basically used up this entire edge. Okay, so that's going to be 10. Now what we do then is that along this path, we're now flowing 10 litres along this path here. Okay, so what we're going to do is we're going to subtract 10 from all of these capacities, because we've now used up 10 litres, for example, out of the 100 from CT. We've also, from SA, we've also used up 10 litres. AB is now fully saturated. Okay, we don't have any more capacity left in AB. Okay, so capacity usually in this context means how much left, or how much of the pipe is there left that can carry more water or whatever it is. BC had a capacity of 20. We're now flowing 10 litres into that. We now have a capacity of 10. Okay, so this path now, we cannot flow any more in this path. Let's now have a look at the other alternative path to go from S to T, which is SADCT. And again, let's look for the smallest or the most restrictive edge, which is edge AD. Okay, so now we need to use the numbers now that are in red as well. So out of the 90, 30, 40, and 90, the 30 is the smallest number. So we're going to subtract 30 again from all these numbers, all these weights. So that's 0, and we're going to subtract 30. So now that becomes 60. 40 minus 30, that becomes 10. Okay, and 90 minus 30 is 60. Okay, so the flow capacity therefore would be 30 along this particular path. Okay, so when I talk about flow capacity in this context, I'm just talking along just the capacity of this path. Okay, so I'll just clarify what I just meant by that. Now the flow capacity of this entire network is the sum of these two numbers. So 10 plus 30 is 40. So therefore the total flow capacity is 40 or 40 liters per minute. Let's have a look at another network flow example, and this one is a far more obviously complicated version of example number 1. But we're doing basically the same thing, except it's just there's a lot more paths to consider. So let's read the question first. So consider the following directed network representing traffic flow. And here's the network there, and the numbers, basic cars per minute on these particular roads. And determine the flow capacity of this network. So that's part A. And part B, we're going to redraw this network showing the traffic flow along each road in order to achieve maximum flow. What that's going to mean is that we need to look at the roads that have excess capacity and basically change the number to reflect the exact capacity needed for each of these roads. Okay, so let's start off then. And what I've done is that I've printed this up on a sheet of paper, and I've got part of a whiteboard here. So what we're going to do first is we're going to consider some of the more obvious paths first, from source to sink, and then consider which edge along those paths is the minimum or the lowest value. Okay, and then we're just going to continue on that way and keep subtracting away from the capacities of these edges until we end up basically saturating the network. So let's have a look at maybe an obvious path. So I'm going to basically account for these paths here. So we have path SAT. Okay, so we've got SAT, and the minimum, you look for the minimum number. Okay, so the minimum number is 270. Okay, so that path can carry 270 cars per minute. Okay, now a pencil is very handy. Okay, pencil and an eraser. They're the two things that you need, and of course a calculator, depending on the values that we're given. So, all right, you'll need one of these. Okay, and obviously one of these. All right, so SAT 270. What we're going to do is we're going to subtract 270 from each of these numbers. Okay, and so we end up then with 30 here for this path AT. Okay, that means now we can no longer use SA. Okay, so that's now basically saturated. Okay, let's try and identify another path. So we could use maybe another. Just think of an obvious one, maybe just straight across. So S B C D T. Okay. There's many ways of doing this, and you don't have to use these paths in this particular order. Just whatever's more obvious to you. So SBCDT, again, the smallest number is 230. Okay, so that means that path can contribute 230 cars per minute from source to sink. So let's write that down. Okay, so hopefully you can see that okay. Yep, I can see that on my camera. Right, so we're going to subtract 230 from each of these edges along this path. Okay, so notice that every time you do that, one of these edges will become 0. That means that we've saturated it. It's there's no more spare capacity in those edges, okay, or on those roads. So now we're going to subtract 230 from each one. So that's going to be 90. Okay, so this one will be 140. Okay, and this one will be 480. Okay, so all right. So we can no longer use path BC. That's now saturated. We cannot. That's no longer can no longer be considered. All right. Let's have a look at another, maybe another sort of obvious path is SEF DT. Okay, so SEF DT. Yep. And let's consider the smallest value. So the smallest value is 260. Okay, so what we're going to do, that means that that's the obstruction, that's the bottleneck. All right, we're going to subtract 260 from the remaining roads on that path. Okay, so that's going to be now 0. So that road is saturated. 440. Right, so that one now is 180. Okay. 270. Okay. 180 minus 260. Okay, notice now that we no longer use the 710, we're using the 480. Minus 260 is 220. Okay, so we still have some capacity, maybe have some capacity left between S and T. Can we identify another path somehow? So we can't use SA, we can't use BC. EF is now gone. Is there another way to get from S to T? Okay, so we could go SB, A, C, DT, sort of a complicated path there, or we can go SE, C, DT. Maybe we'll do that one. Okay, SE, C, D, and T. All right. Right, let's walk along this path or drive along this path and see which is the lowest number. In fact, we've got 180 there, 180 there, 140 there, 220. So 140 is the bottleneck. Okay, so we're going to saturate that one. That's now to capacity, and that now is 0. Okay, so that path now can no longer be considered, and we're going to subtract basically 140 from all these other numbers, all these other capacities there. So that's now 40. Okay, that one there is now 40 as well. Okay, and that's 0 there, and what else have we got? 220, so that's 80. Okay, so okay. All right, now the question is there any other way to go from S to T? Can we think of another way? We can no longer use this edge here. We've got 40 here, 40 there, but we can't go here anymore. So these two roads, SC and EC, are no longer available or can no longer be used. But we can't go S. Can we go SB, A, C? No. Oh, hang on. We can go SB, A, T. Okay, so it's very, very important that we consider every option. SB, A, T. Yep. So we've got a capacity of 90 there. B, we've got 290. So we haven't even used that one, that particular road yet. We've got an AT is 30. So we've only got 30 left on that path. Okay, so we're going to subtract 30 from that. So that's gone. Okay, AT is saturated. We used up all that capacity. Okay, and we're going to just subtract 30 from each one. So that's now 60. And 290 minus 30 is 260. Okay, so I might just... okay, so you'd agree that a good sharp pencil is very important. Okay, because like I said, you may make a mistake here. So it's very easy to fix. Okay, and I think that's it. That's all the paths considered. So adding all those up, so 270 plus 230 plus 260 plus 140 plus 30, we got a capacity of 930. Okay, so that's the flow capacity of this particular network. What I'll do is I'll do part B as a second video because it's, I don't want the videos to be too long. And what we're going to do is we're going to redraw the network so that we're not going to have any spare capacity. Continuing on now with example number 2 for network flow. In the previous example, we determined the flow capacity of this network by considering the various paths. So you might recall this from the last video. Okay, so these were the various paths that we had identified and considered the capacity of each path. Okay, and then we ended up with this diagram. Okay, and with the spare capacities that are left over basically on each of these roads or each of these edges. So if anything with a 0 means that road has been totally consumed. Okay, so but totally saturated with cars. Anything that doesn't have a 0, so for example SE, okay, we've got 40. That means that's 40 cars per minute of spare capacity. In other words, SE is too big. That road doesn't have to be that big. There's a few others as well. FD is way too big. I mean, we're 270 cars per minute too large, in fact. So what we're going to do is we're going to redraw or basically putting weights on each of these edges that reflect the exact capacity needed to get the maximum flow of a 930. So that was what we had determined in the last example. Okay, so again, I'm just going to use a red pen. I'm just going to draw over this diagram. So let's consider all the edges. So again, SCFD, T. All right. You need to consider the original capacity. So SC was originally 440, but after we did the whole analysis of determining the flow capacity, we found that we were 40 cars per minute too big. So what we're going to do is we're going to subtract 40 from 440, and that'll in fact be our new capacity. So the capacity that we actually need for SE is in fact 400, because that's actually what's being piped through SE at the moment. That's the number of cars that are going through SE. The road is big enough to handle 440, but there's only 400 going through, so SE only has to be 400. EF is 0, which means that it's at capacity. FD, so 530 minus 270, we've got 260. Okay, that's our new capacity there. And we've got DT, so starting off at 710, we end up with 80 cars per minute spare. So we end up with 630 is the capacity that we need for DT. Okay, AT is 0, so that's at capacity. SA is 0 as well. SB got 320 starting off with. We end up with a spare capacity of 60. So 320 take away 60 is 260. Okay, so 260 there. BC is at capacity. In fact, AC never even got used. So AC is totally redundant. In fact, that capacity there, in fact, can be 0. AC never got used at all. Now, you may end up with a slightly different answer. It doesn't actually matter. It really depends on which paths that you considered. If you did consider SB, AC, DT, then AC would have been used, and then you might have some slightly different numbers. But this is it's not the only solution, but it's one of many solutions, okay? So AC didn't even get used at all. So we've got 230 spare. It's a spare road. We can even get rid of that road altogether. CD is 0, so that can stay at 370. EC, we start off at 180. We end up with 40 spare, which means that the actual capacity that we need is 140. Okay, I'm just trying to think if there's anything else. Yep, we've got BA, 290 starting off with. We end up with a capacity of 260, which means that there's actually 30 cars per minute going through BA there. All right, I think we've considered all the edges, just make sure we count through. So SC is done, yep, that's done. EF, all the ones that have 0, make sure, well, we don't have to do anything there. CD's fine, DT we've considered, BC we've considered, yep, I think that's done. And that's our new network diagram. We can transcribe that onto a brand new one. So I could have copied it onto this sheet there, but I think as long as you can show that, you know, these are the new capacities. These capacities will ensure that the maximum flow is still reached without having roads that are bigger than what is required. Let's have a look at this network flow diagram. And what we're going to do with this one is first of all, we're going to determine what the maximum flow of this network is from A. Okay, so basically A is the source and Z is the sink. So we need to determine first of all what the network, what the maximum flow capacity of this network is. But secondly, what we're going to do is we're going to also choose a particular edge, or any edge, but we need to justify it. Which edge would you increase to increase the total capacity of the network? Okay, so one of the edges will have more of an effect on increasing the flow capacity of the network than say other edges. Okay, so let's work out first of all what the maximum flow capacity of this network is. I mean, look, you could use the minimum cut maximum flow theorem if you like, but we're just going to do this the algebra way, or the numerical way. So first of all, let's have a look at paths from A to Z. Okay, the most direct path is AZ, obviously. So, and that can flow 18. Okay, so we subtract 18 and it becomes 0. Okay, another slightly less direct path is AXZ. Okay, and that can flow 27 because the smallest number between the 30 and the 27 is obviously 27. So it can flow 27. So that becomes a 0 and the 30 becomes a 3. So that means that AX still has a little bit of spare capacity left. Okay, chances are that probably one of these edges might be a little bit too big. Some might be a little bit too small. So that might give you a clue as to which edge you would choose. So there'll be one of these edges will be small, will be actually too small. In fact, you'd be saturating it quite quickly, and it would appear that it would need more capacity on that edge. Alright, let's have a look at some other paths from A to Z. We've got A WXZ, but that's 0 because XZ is already saturated. We've got A WYZ. I guess we have some capacity there. Okay, A WYZ. Okay. So 62 is flowing from AW, W to Y is 41, Y to Z is 36, so we take the smallest number, which is 36, and then what we do is that we subtract 36 from 41, okay, and that gives us a remaining capacity of 5, and 62, where are we, 62, okay, we're going to take 36 away from that, and we get 25, okay. And obviously 36, we take 36 away from that and we get 0. So that's it. We've now saturated all the inflows to Z. Okay. So in fact, one of the paths, actually two of the edges did not get used at all. In fact, so WX and XY didn't even get touched. So increasing WX or XY is actually not going to make any difference at all because we're not even using them. So we'll definitely need to increase the capacity of an edge somewhere. We could increase AW, but well, we've already got spare capacity there, so there's probably no point anyway increasing that one. We'd probably need to increase one of the ones that are 0. Okay, so in other words, if we increase the ones that have a green number other than 0, higher than 0, so increasing WY probably won't make too much difference there. Okay, we could even maybe increase XZ, okay, because increasing XZ we could in fact take advantage of AW because AW has the most spare capacity, okay? And WX has quite a bit of spare capacity there, okay? In fact, well, XZ, I would increase XZ by 23, okay? Because we then have a path AWXZ, okay, which will in fact increase the flow by 23, okay? So that way then we're taking advantage of these two edges that have a lot of spare capacity left, okay? And this edge here, XZ, obviously can be increased. So that would be the one edge that I would choose. If you increase YZ, for example, you need to say to yourself, well, if YZ is increased, we can have a path AWXYZ, but the XY is quite small, and that's going to limit it to just a sort of just an extra 9 units of flow. So I would choose, okay, XZ to increase, okay, and because, okay, AWXZ has the potential to flow another 23, okay, because the path, okay, AWXZ, right, has the potential for another 23 units of flow, okay, and I would increase XZ by 23. Okay, so in other words, instead of it being 27, I would make that 50. Okay, so in other words, if I was to make that edge originally 50, all right, and then we took 27 obviously away from that, okay, that would leave a spare capacity of 23. Okay, so this is the path AXZ, so AXZ. In fact, in doing so, you would also increase, you would actually use up this capacity here as well. So going back over that, I could actually use up this one here. I would actually increase it by 26, in fact. So just think, sorry, I'll just do that in red. Okay, so that's why it's good to think about this a little bit, to think, okay, is there anything else that could potentially flow into it? So let's make that then 53. All right. So let's see what happens now. So AXZ, okay, we would flow 30. In fact, we could flow the whole 30 into that, and then you'd end up with 23. Okay, we'd end up with 23 units of flow of spare capacity. Then this AWXZ could flow the entire. We could saturate the entire edge, or in its entirety. We can saturate WX and make that 0 as well. Okay. I'm just going to pause the video. I'm going to redraw this diagram now with the 53, and then we're going to see how just increasing that edge would increase the flow. The other thing that just got to work out as well, and sorry I didn't do this earlier in the video because I was really focused on looking at this one edge to increase, is the total, the flow capacity of this network, which is 81. All right. So increasing the edge XZ, what does that do then to the flow capacity of the network? Okay, so I'm just going to pause the video, then I'm going to flip the board around. Okay, I'm back. Okay, I didn't have to flip the board around. All I did was just redrew the weights of the edges back in again. Except this time I just changed XZ, and it's now 53. So let's see then what happens to the flow capacity of this network. Remember, originally it was 81. All right, so let's compare our sort of our new network with the old. All right, let's have a look at the paths from A to Z. We have path AZ, which is 18, of course. So that hasn't changed. Okay, so we're going to subtract 18 from that. All right, now we've got AXZ. Okay, AXZ can flow, in fact, a full 30 All right, so we're going to subtract 30 from everything now. So that becomes 0, and that becomes 23. All right. Now we can look at AWXZ. Okay, and AWXZ can flow 23, in fact, since we've increased XZ. So that becomes 0, that becomes 0, okay, and 62 minus 23, my brain's getting a bit tired now, so that's going to be 39, okay. Do we have any other paths from A to Z? Yes, we do. AWYZ. Okay, AWYZ. We have 39, 41, 36, so that's going to be 36, obviously. And we're going to subtract 36 from everything, so that's 5 and that's 3. Okay, and lastly, do we have any other spare capacity? No, we don't. There's no other way to get from A to Z. So adding up these numbers, so we've got 18 plus 30 plus 23 plus 36, and we end up with 107. Okay, so that's an increase of 26 extra units of flow. Okay, so that's most certainly made a significant difference to the flow capacity. Here's another interesting network flow problem, and one that actually involves a little bit of algebra, in fact. And just another clarification that I need to make, and it's to do with the term maximum flow of a network, when I talk about that concept or that idea of a maximum flow. Let's just read through the question quickly. The following network shows the flow along each edge that would achieve maximum flow from the source S, so that's this one, to the sink T. Okay, find the values of A, B, W, X, and Y. Okay, so these are the pronumerals here in red. What is meant, first of all, by maximum flow of a network? Okay, so maximum flow implies that the inflow to every vertex is equal to the outflow of that vertex. Okay, so I might just make that point here, and you could note this down somewhere. So maximum flow of a network is where at any vertex, okay, other than the source or the sink, okay, the inflow equals the outflow. Okay, I think that's a very, very important point to make. Okay, so if this term ever does come up, okay, and there is a chance that it could come up potentially. If you've seen this in any textbook or you've seen it in a problem somewhere where they talk about the idea of maximum flow means at any vertex. Say for example, pick I don't know, vertex C. The inflow is 15. The outflow is 10 plus Y. Okay, that means that whatever's going into C is exactly what is coming out of C. Okay, that's the same with any vertex. Now, what happens then at the source and the sink? At the source and the sink, the outflow of the source equals the inflow of the sink. Okay, and once that is achieved, in fact, that's when maximum flow is achieved. Okay, when you're doing the maximum flow problems or you're trying to work out the maximum flow of a network, that's when you get no excess capacity. You know, when you do the whole subtraction and you sort of you consider a path and you take away whatever the lowest number is on that edge, on that path, you should be getting zeros everywhere, in fact, once you do the whole exercise. Okay, so I'm just going to rub out here what's in blue, so actually need some space to do some working out. All right, let's do some mathematics. All right, now quite a few unknowns. In fact, oh, look at this one. This edge SB is 2A, 2 lots of A. So in other words, whatever SB is, it must be double the weight of whatever BE is. So that makes it a little somewhat interesting. Let's choose a vertex then that we could probably, work out quite easily. Let's check vertex A. All right, so vertex A, the inflow is 20. Okay, so at A. Okay, The inflow is 20, and it equals the outflow, which is 8 plus B. Therefore, B is equal to 12. Okay, so I'll put that answer there. All right. Now that we've got that, could we work out another pronumeral, okay, another edge? So we've got, let's say, vertex D. We've got a 12 going in, we've got a 5 going in, we've got a W going in, we've got a 35 coming out. So at D, okay? So 12 plus W plus 5 is equal to 35. Therefore, W is equal to 18. All right. Okay, we're slowly working this out. Any other pronumerals that you think we could work out? Could we work out the Y here, perhaps? This one here at vertex C, maybe? Okay, hopefully you've identified that one next. So what I'm doing is you're targeting the vertices that only have just an unknown outflow. But vertex B has unknown inflows and outflows, so that makes it probably much more difficult. In fact, we'll probably have to leave vertex B till the very end, in fact. But let's see. So at vertex C, the inflow is 15, and the outflow is 10 plus Y. Therefore, Y is equal to 5. Okay. Now, we could either work out vertex X, but that's going to be pretty difficult because we've got at vertex E, 10 plus A is equal to 5 plus X. That's going to be too difficult. However, we could then go to vertex B, okay? And vertex B now only has one unknown. You've got a 2A and an A. We can still work that out as long as it's the same pronumeral. So at B, okay, what are the inflows at B? We've got 3 inflows. We've got an 8, a 5, and a 2A. So 8 plus 5, yeah, plus 2A is equal to the outflow. Now we have the W is known now, so that's 18, okay, plus A. Okay, that's just a regular equation with with the same sort of same pronumeral on both sides. So we can collect like terms and do all that other fun stuff. Let me just clean this up a little bit. So 13 plus 2A is equal to 18 plus A. Okay, if we move the plus A over, so solving this equation, 2A minus A, we have A on one side, 18 minus 13, so we have A is equal to 5. Okay, so that means if A is equal to 5, what's 2A? 2A must be equal to 10. Okay, so we've worked out basically 2 edges, okay, almost at once. Now finally, we can use the idea, we can either use vertex E, now that we have the inflow, okay, so we have the inflow of 10 and 5, so it gives you 15, the outflow of 5, well, X is going to be 10, or we could use the rule that basically, if you want, you could probably do this even. If you do a cut, right, the capacity of that cut there, okay, equals the capacity of this cut here. In fact, so basically the outflow will equal the inflow. Either way, it's fine. Doesn't really matter. In fact, let's see where I've got some space to write now. The problem with these little whiteboards, I run out of space very easily. Okay. Why don't we use that rule? The outflow equals the inflow. So 20, okay, plus 10 plus 15 is equal to 35 plus X. So 20 plus 10 plus 15 is 45, is equal to 35 plus X. Therefore, X is equal to 10. And we've now worked out all the pronumerals. In this example, we're going to determine the capacity of the cuts shown, and a cut in a network flow diagram separates the source from the sink totally. In other words, there should be, when a cut is made, there should be no way or no path that can get you from S to T. So let's see, maybe let's have a look at the first two sort of obvious ones. So we've got the blue cut here, okay? that cuts through edge SA, SB, and SE. Okay, and these three edges, if they're cut off, will most certainly cut off the source from the sink. And so the capacity of the blue cut, so we add up the weights of the edges that the cut goes through. So 270 plus 320 plus 440. The capacity of this cut is 1030. Let's have a look at the red cut. So that's another cut that obviously separates the source from the sink. And that's a total separation, not a partial separation. Again, there's three edges that it passes through, and all three edges are necessary to be cut off in order to separate the source from the sink. So 300 plus 370 plus 530, so that gives us 1200. Okay, and let's have a look at the purple cut here. Now, the purple cut does cut off part of the network, but it's not a total separation of S from T. This purple cut here only cuts off part of the network. There is still a way to get from S to T. So this purple cut here, this is an invalid cut. Okay, so I might just put here as invalid. Okay. So that we can't measure that one. We can't measure the capacity of that because that doesn't count as a cut. A cut must separate the source from the sink. And that leaves us now to the last cut, so the green one here. And it passes through quite a few edges. So it passes through this edge here, this edge here, this edge here, this edge here, and this edge here. In fact, one of the edges though is unnecessary and not needed to be cut. In fact, if you look at edge AB, okay, this edge here, it's actually not necessary for this edge to be cut. I'll explain why. Let's have a look at each of the other edges. SE. If we do not cut SE, but cut off everything else, there is a way to go from S to T. In other words, let's say this little part here was not cut off. We can go from S to E to F to D to T. There is a way to get from S to T. Okay. Notice that I'm focusing on eliminating any possibility of getting from S to T, but not by cutting unnecessary edges and extra edges that do not need to be cut off. Okay, I think that's very important to note that. So this is a necessary one. So I might just put an X on that to say that that is most certainly a necessary edge. AT, is that a necessary edge to cut along the green line here? In fact, if we don't cut this off, then there's a way to get from S to T via A. We can go S, A, T. So this one is most certainly a necessary cut as well. Let's say we don't cut off AC. So let's say this is open at this point here. And everything else is cut off. So that's cut off, that's cut off, that's cut off, and that's cut off. We can go S, A, C, T. So this one is a necessary cut. Let's say then we don't cut off this one here, okay? So edge AB, let's say we didn't cut this off, but all the rest were cut off. Is there a way to go from S to T? Well, let's see, we can't go this way. We can't go through A, so we can't go this way or this way, okay? And we can't go this way either. In fact, we don't even get to this cut here. So everything else is cut off, but we're not even able to get to this point because SB also happens to be a necessary or a critical, well, maybe you can use the word critical, but it's a necessary cut as well. This one here is unnecessary. In fact, this roadblock, this roadblock, this roadblock, and this roadblock here are enough and sufficient to cut off S from T. This one here is not necessary and we're not going to count that, okay? That also goes for cuts in on edges that go in the opposite direction. In other words, going from sink back to source as well. So let's add up these four edges then. There's these four necessary roadblocks. That's just another word that I like to use. So 440 plus 320. We're going to ignore this one because it's not a necessary cut. We can omit that one. 230 plus 300, and we have 1,290. Okay, you notice that each of these three valid cuts, each of them, the capacities are different, in fact. And there are other cuts that we could make as well. And later on, when we talk about the minimum cut, maximum flow theory, we'll find that there is a cut that will, in fact, give you a flow that is, in fact, the minimum flow, the minimum cut that'll actually give you, determines the maximum flow of the network and the flow from source to sink. Let's look at another example where we calculate the capacity of any particular cut in a flow diagram. I think it's important to note though that a cut does not determine how much flow there's actually occurring. What it does calculate though is what is the theoretical capacity at that point or at those set of points in a network. So each of these cuts, for example, so I've drawn 4 cuts here in this network diagram. Each of these cuts will give you a different value in terms of the flow capacity at these points. So cut 1 cuts edge SA and SB, for example. That doesn't actually mean that there's 25 plus 40 units of flow happening at that point. It just means that that is in fact the capacity of those pipes, or the roads or lines or whatever at that point in the network. Okay, working out the maximum flow of the entire network is something else. Okay, so all we're doing is we're just calculating again just the capacity of these 4 cuts. Okay, let's have a look at cut number 1. Okay, so cut number 1, okay, cuts off the flow from source to sink, okay, by cutting basically that edge there and that edge there. So clearly you can see that cut number 1 is a valid cut. Okay, I'm just going to draw these back in. Okay, and all we do is we just add the capacities of the edges that are involved in that cut. So 25 plus 40, the value of that cut is 65. Let's have a look at cut number 4. Now notice that I've skipped these 2 cuts in the middle because they take maybe potentially a little bit more time, just a little bit more analysis involved with those. Cut number 4 is another obvious cut that cuts off the source from the sink. Okay, and that one is the capacity of that cut is 30 plus 50, which is 80. So notice that cut 1 and cut 4 will isolate the source from the sink, but they're totally different values. One's 65 and one's 80. So that tells you the capacity of the size of the pipes, but that doesn't actually tell you how much is actually flowing or what the maximum flow is in the entire network. Okay, that's the maximum flow, or the minimum cut maximum flow theorem. Okay, what about cut, let's say cut number 2. Okay, so cut number 2 cuts off SB. Okay, so what I might do is I might just remove a little bit of the whiteboard marker ink there. Okay, is there another path to get from source to sink? Yes, there is, through SA and AT, and also SA, AB, and BT. Okay, so you will need to definitely cut this point here. Yep, so the cut through SB is valid. AB, the cut through there is needed, okay, to cut off the source from the sink, and also this edge here, AT, also needs to be cut. So just remove that. So you can see clearly that by putting in these cuts, okay, you will isolate the source from the sink. There is no flow possible. So what we're calculating is the sum of these pipes, okay, or these edges. Okay, so that'll be 40. Okay, plus 15 is 55, plus 30 is 85. All right, what about cut number 3? Okay, so cut number 3 cuts off SA, okay, cuts AB, and also cuts BT. Now, let's cut SA first. Okay, by cutting off SA, it cuts off the inflow to A, which automatically cuts off the outflows. Okay, so AB is actually not a relevant cut. It's not even, it's an unnecessary cut. You can't include this 15 in the cut. If you're cutting off the input to a vertex on the way to the sink, all the outflows are automatically cut off anyway. So that is not valid. We don't actually include this, this edge here. But we do need to include this edge, BT, because if we don't, there is a path from source to sink, SB, and then BT. So if I just take a little bit of ink off there, okay, have we cut off the network completely, entirely? Yes, we have. If anything tries to flow from S to A, whoop, stops there. So these edges automatically won't get anything, so that the flow will be zero there. And also through vertex B, SB, well, there's sort of a roadblock there, nothing will get through. Okay, so it's actually just these two that we need to add up. Okay, so it'll be 25 plus 50 is 75. Okay, and so these are the capacities of these four cuts. Here is another example of calculating the capacity of various cuts in a flow diagram. Okay, the important thing is to determine which of the edges are actually unnecessary to be included in the capacity of the cut, because it's like having a double roadblock on a road. You only need the one, you don't need two. So what I'd invite you to do at this point is probably pause the video, okay, and try to work out the capacity of the four cuts, unpause the video obviously, and then compare your solution to my solution, okay? All right, so what I'm going to do now is I'm going to calculate probably the two simplest cuts first. Cut number one, okay? All three edges are coming from, basically emanating from the source. So all three of these edges will need to be cut. So SA, SC, and SD will most certainly need to be cut. So 10 plus 20 plus 30, that's going to be 60. Okay, so I'm starting off with the most basic cuts, okay, first. Cut number 4 is also a very obvious cut that cuts off the source from the sink. Okay, and again, all three edges here are necessary. So we have 120 plus 90 plus 110, and that's going to be 320. Okay, the capacity of that cut. Two very different numbers, isn't it? So if this cut tells you that the capacity of the pipes or the roads or whatever is a value of 60, this cut's 320, surely the flow cannot be more than 60, surely. Because if this part of the network can only handle 60, say 60 cars per minute, this part of the network can handle 320, but if this part of the network's feeding in 60, well then that means that that at this point, at least from what we've determined, we can't be any higher than 60. We probably could be lower than 60. There could be an area of the network that is in fact less. Anyways, that's to be talked about later on. Let's have a look at cut number 2. Cut number 2, we have cutting AB, it's cutting AC, DC, and DE. At this point, you should probably determine that AC is in fact unnecessary. And the reason for that is AC is an outflow of C, but we're already cutting off the inflow to C. In fact, let me demonstrate this. If I cut the network there, okay, and I cut the network, say, I'll just cut it near the edge, so let's say there, okay. So by cutting off the network from AB, we're in fact cutting off this path here and this path here, or this edge here, okay. There is still a way to get to C though via D, so we have to cut this edge here as well. So what we've done is that we've effectively isolated C, so therefore AC is not necessary. It's not a necessary cut, and it cannot be included as part of the calculation of the capacity of that cut. Okay, so we've got the 60. Okay, so there's actually 3 here, 60 plus 20 plus, what have we got here, 50. Okay, so, and that gives us 130 as the capacity for cut number 2. Okay, all right, might just draw these back in, and okay. What about cut number 3? Okay, cut number 3, hopefully you've determined that BC, edge BC, is in fact unnecessary. BC and BT are outflows of vertex B. So by cutting off the inflow, we've automatically cut off the outflow, so we cannot include 80 in the calculation, okay? So this is what you should be doing every time. If you do a cut in a network, you should be analyzing each of the edges that have been cut to determine if one of the cuts is in fact unnecessary or in fact redundant, okay? Because if you've cut off the inflow to that vertex, that automatically cuts off the outflows, okay? If a vertex has multiple inflows and they've all been cut off, then all the outflows have been cut off as well, okay? But vertex B only has one inflow. By cutting that, it's automatically cut off these two outflows there, okay? CT, we have to cut that, so certainly that's got to be cut off, and also CE has to be cut off as well, because we have a path to T, SCET, okay? So we definitely have to cut that off there, okay? And SDET, okay, we definitely have to cut this edge here, this edge DE as well, okay? So adding them all up now, so we've got 60, okay, plus we missed the 80, plus 90, okay, plus 100, plus 70, okay, so there's actually four edges that have been cut that need to be included, okay, so, and that gives us 320. Let's have a look at a simple example of the maximum flow minimum cut theorem. And I guess it's a bit of a strategy in understanding some of the ideas in networks. If some of the concepts seem complicated, it's always a good idea to try and consider very simple cases first. So the most sort of simplest of networks that you can come up with, or any particular examples that you can have a look at. Try to see if you can understand the concept just using very, very simple networks, and then that can be extended into more complicated networks. So let's have a look at this network here. We have basically just four edges. There's the source, sink. Another word for source and sink is start and finish. And we've got basically two ways to go from source to sink. And let's do part A first. So we're going to determine the maximum flow of this network. We're going to determine it numerically. Okay, we've done this before. There is a previous set of videos that will look at examples of maximum flow or flow capacity using numerical methods. So let's have a look at part A. Okay, there's two paths, isn't it? We've got path SAT, and we've also got path SBT. Okay. So this is simple enough that you can practically work it out just by looking at it. SAT, really, you've only got a capacity of 1, because SA is really the impediment or the obstruction, really, or the restriction on the flow. AT has greater capacity than SA, but AT is not going to be used to full capacity, so it's only going to be 1. So that saturates this path SAT. SBT, we've got 3 and 4. Its capacity is going to be 3 because BT is not going to be used to its full capacity. Okay, because SB is it's limiting BT because it's only 3. So that gives us a total of a flow of 4. Now let's have a look at it graphically, or using the maximum flow minimum cut theorem, which is a graphical method. And let's cut this network, or let's consider the various cuts that we have. So let's look at sort of the more obvious cuts. So we've got that cut there, okay? We've got this cut. I might actually use some different colors as well, just so it doesn't get too complicated, but we've got this cut here. Now we've also got this cut this way. Okay, and we also have a cut this way. Okay, so you've got the blue cuts and the green cuts. So okay, so we can see that I might actually label these cuts. Let's call that cut A. Let's call that cut B. Okay, let's call this one cut C and cut D. Okay, so cut A is equal to, now you sum the edges. Okay, so all of these cuts are valid cuts, of course, so each one of them will cut off the source from the sink, so that they'll be isolated from each other. So cut A is 1 plus 3, which equals to 4. Cut B, okay, we've got 2 plus 4, which equals to 6. Likewise, we've got cut C, okay, you've got 3 plus 2, that's equal to 5. And cut D, okay, and cut D is, where is it? Yep, 1 plus 4, and that's also equal to 5. So the cut that has the minimum capacity is this one there. So therefore, maximum flow of this network is equal to 4. Okay, so you can actually use either theorem to work it out. Sometimes it's actually easier to work it out numerically than it is to work it out graphically, but either way it's important to be able to work out the maximum flow using both methods. Let's now have a look at a slightly more complicated version of example 1. So this is example 2 of maximum flow minimum cut theorem. So consider the following network flow diagram. It's almost identical to example 1. The only thing is that I've just added an extra edge here, this edge BA. Okay, and we're going to do the same thing or something very similar to example 1. So we're going to determine the maximum flow of this network. We're going to determine it first of all numerically, and then we're going to determine it using the maximum flow minimum cut. Now, with the next example and do example 3, I'm going to reverse these two around. In fact, we're going to use the maximum flow minimum cut theorem first, and then we're going to verify the maximum flow using numerical methods to see that it correlates. Okay, let's have a look at part A first. So let's identify the various ways of getting from S to T. So always, whenever we're trying to work out maximum flow of a network, especially if it's to be done numerically, you need to identify the various paths first. So this is the various paths from source to sink. So we have SAT. Okay, and SAT, it's going to be 4 because along this path here, the smallest capacity is 4, so that limits the entire capacity of that path to 4. So that would be, so we're subtracting 4 from each of these numbers, each of these capacities, and so the new capacities now are 0 and 6 once we saturate path SA. Another path is SBT. Okay, and its capacity is going to be 1 because BT is the smaller of the two capacities and it's the most restricted or the most restrictive edge. And we're going to subtract 1 from each and we end up with these numbers there. And the last path that we can identify from S to T is SBAT. Okay. And we compare the three capacities of the three edges. So we got edge SB is 4, we got a 3, we got a 6, so it's going to be 3. And we're going to have a maximum flow capacity of this network will be 8 from source to sink. Okay. Now let's have a look at part B, which is using maximum flow minimum cut. Okay, and we need to identify the various cuts, and shouldn't be too much different from the last example. Okay, so we have this cut here. Okay, and let's call that cut cut A. Okay, we've got this cut here. Okay, and that's cut B. Sorry if you probably can't see that. Let's call that cut B. Yep, it's better. Okay, any other cuts that you can identify? We can probably again do sort of a crisscross cut again. So maybe we can do a cut this way. So yeah, and let's call that one cut C, and we can do one this way as well. Okay, so and there's cut D there. Okay. All right, so let's consider these cuts now in order. So, or
really in any order that you like, it doesn't really matter. Cut A, okay, so cut A cuts through SA and SB. Always remember that a cut has to cut an edge that actually flows away from the source, okay, and toward the sink, not in the opposite direction. So cut A, both of them are flowing away from the source, so that's going to be 4 plus 5, and that gives you a flow of 9. Cut B. Okay, so cut B is 10 plus 1, and that gives you a flow, the capacity of that cut is 11. Okay, so cut C. Okay, and so cut C cuts through this one here. Okay, so SA. Okay, and notice that it cuts through BA, but BA is also flowing from away from the source toward the sink. So we actually add that 3. So plus 3 plus 1, and that gives us 8. Now let's have a look at cut D. Okay, cut D, we don't include BA, okay, because BA is in fact flowing in the opposite direction. Okay, so cut D, so this one here, SB, 5, won't be adding 3, but we'll be adding 10. So it'll be 5 plus 10, which gives you 15. So cut C is the lowest of all 4 cuts, and so this would be, this cut here would represent then, therefore, the maximum flow of this network. Let's have a look at another example of using the maximum flow minimum cut theorem to determine the flow capacity of a network. And this time around, though, compared to example 1 and example 2, we're going to use the maximum flow minimum cut theorem first to determine the flow capacity of this network. Then we're going to verify that answer using a numerical method, so it's kind of back to front compared to those other 2 examples. And then finally, if you had to increase one edge, which edge would you increase to increase the flow of the network? So now, just to expedite this video, if you like, you can, if you want to pause the video, have a go at the question for yourself. By all means, do so. I'm going to go through the solution shortly. So, in fact, if you're going to pause it now. All right, okay, unpause. I'm going to go through solution A, for part A at this point. So, there's quite a few cuts that I've identified, so you can compare it with your solution. Okay, and so I've identified 7 cuts. Okay, so we have, I'll just run through the cuts quickly. So we've got cut A, okay, we've got cut B here, cut C. Okay, we've got cut D, cut E, cut F. Okay, now cut F is I've actually put circles there for a reason. I'll show you why later. Then we've got cut G. Okay, which just, if you just trace that, that's up through that part of the diagram there. Now, determining the capacity of each of the cuts. Cut A, you just add up basically the edges, the capacities of the edges. So cut A, we've got 5 plus 9 plus 4 gives you 18. Cut B gives you 19, so it's just this cut here, 10 plus 2 plus 7. Cut C is 13. Okay, so can we see why it's 13? We've got 7 plus 2. Now we're going to add, we can't include the 6, we can't include AC for cut C. Because we're cutting SA, we're cutting the inflow to A, that automatically cuts the outflows. So that's in the wrong direction. So it's going to be 7 plus 2 plus 4, which gives you 13. Cut D, okay, so we're cutting this edge here, and this edge here, and we get 17 when we add those up. Cut E is a fairly large cut, this one, so it's 7 plus 9 plus 4. Gives you 20. Cut F is this one here, so it's 5 plus 2 plus 4. Again, for the same reason as before, Cutting off SA is upstream of A. That's the inflow to A. It really cuts off the outflow. So we include SA but not AC, and we get 11 when we add those 3 edges up. And then cut G, this one's way off. It's 32. I think it was 7 plus 9 plus 6. Okay, plus 10. Yep. So we have to cut off all these edges there to cut off fully cut off the source and the sink, and we get 32. Okay, so by the maximum flow minimum cut theorem, the flow capacity of this network is 11. So let's have a look at part B, and I've already done the solution for part B. So using the numerical method. Okay, this is my solution for part B. I've identified first of all the 3 parts, or at least the paths that are possible. There's another path that is possible, but I didn't include it, which is path SACT. You'll see why shortly. SAT is 4, so we have, I might just rub this out here. So SAT is 4. Okay, so that means then that we subtract 4 from both of these numbers, so from 4 and 10. Okay, and AT then is reduced down to 6, and SA is now saturated. It's now 0. Okay, we have SBT. We have a 5, inflow to B is 5, the outflow of B is 7, so it's the minimum of the 2. So it means 5 is flowing through SBT, which means that we can subtract 5 from both of these edges. SB now is 0, BT is now 2, and so we get 5, a capacity of 5 in that path. And path SCT, okay, you got 9, inflow of C's. In fact, we've got flowing in, well, it's actually 6 and 7 flowing into C, but we've only got 2 flowing out really. Anyways, SCT is 2, that's by far the smallest of the numbers that are entering into C. So its capacity is 2. Okay, so the maximum capacity then of this network is 11. All right, so what then could we do if there's one edge that you would choose to increase? Which edge would that be? I would be looking at the edges that are zeros. Okay, so out of those 3 edges, I think SB is probably the least effective one to increase, because there's only one way for the flow from to go from S to B, which will be from B to T. So these 2 edges are fairly close in terms of their capacities. So increasing SB, if you had to widen that road or increase the diameter of that pipe, you're not really increasing the flow all that much. But we can see here that the inflow to A is 4, but the outflow of A is quite large. So we have a capacity of 6 here, and we also have a capacity of 6 here as well. So we've got 12, in fact, that we could use up. But then SCT is also quite a small number here as well. So I could increase SA, I guess, and in fact, if I was to just increase that, say to 10, okay. So if I made that 10, I would then be able to feed another 6 units of flow through AT, and all the others would then be saturated. So that's one possibility. So that would increase then the flow capacity from 11, adding an extra 6. So from 4 up till 10, that would make the flow capacity of the network to 17. Or I could increase CT to 9. Okay, so remember that we've got 9 feeding into 2 there. If we increase that to CT to 9, then that would allow SC to be used fully, or fully saturated, and then we'd get the flow capacity to 18. So I dare say that increasing CT to 9 would probably be a good edge to choose to maximize the flow capacity. So that would be most certainly the one that I would widen. It also happens to be the one that's the smallest edge, but that doesn't necessarily mean that it's the most ideal one, but it just so happens. One other thing I just want to quickly share with you is when we determined part B, we got 11. These edges here have zeros, so that one there and this one here, these edges are zeros. If you have a look at F or cut F in this in example A, part A of this example 3, example F, cut F cuts through this edge, and this edge, which correspond to, and I might just fold this here because I think it's really good for you to see this. Okay, put them side by side. Okay, so this is part B. Okay, this is part A. You can see here that the 0 on this is part B, where we got the capacity of 0 corresponds to this cut here, or this edge that's been cut here. This 0 CT happens to be this cut here, and this 0 SA happens to be this cut here. Okay.
In this video, we're going to talk about the connection between the flow capacity of a network and the minimum cut, equaling that maximum flow, and also determining the minimum cut by working out the maximum flow first, and then by doing that you can work out where the minimum cut actually needs to go. So let's work out the maximum flow first of all using numerical methods. Okay, so let's identify some potential paths. So we have S, D, E, T. Okay, so I might just keep a tally here. Okay, so S, D, E, T. Okay, and we've got a flow of 4. Okay, so that becomes 0. Okay, so we're subtracting 4 from everything. That becomes 3, and that becomes 2. Okay, so that's now gone. We can't use that anymore. Okay, so another path that we can take is S, C, E, T. Okay. Okay, so SCET, there's a capacity of 2. Alright, that path capacity is 2, SCET. So we'll subtract 2 from everything, so that becomes 0, and that becomes 4, and that becomes 1. Okay. We have another path, which is SCBT. Okay, we also have SCEBT, but we'll take paths that are a bit more direct. So maybe SCBT. Okay, so SCBT, we have a capacity of 1. Okay, so it's the lowest number. So that's 0, that becomes 4, and that becomes 4 as well. Okay, so that's a capacity of 1 for that path. So this edge here, SC and SD, have now been saturated. We can no longer use those two edges, sorry, for as part of a path from S to T. So the only last edge that we can use really from the source is SA. So we have two options. We've got SABT and we've got SACBT, in fact. So let's look at maybe SABT first. Okay, so SABT, we have a capacity of 1. Okay, so that 4 becomes 3, and that becomes 6. Okay, and the actually we do have a path SAC. Okay, EBT. Okay, it's a fairly complicated path. We also have SACBT as well. Actually, let's do this one. So SACB and then T. Okay, so SACBT, and we have a capacity of 2. Okay, so that's 0. Okay, so we're going to just subtract 0 from all of these, so that's 4, that's 2, and that's 1. Okay, and that's it. Okay, Okay, so let's have a look at the edges that are now 0. Okay, so we've got this edge here. Okay, we've got this edge here, this edge here, this edge here, this edge here. Okay, and I'm just trying to see if there's any others there. Actually, B never got used at all. All the others have some capacity there. So SA has a capacity of 4. DC didn't even get used. CE still has capacity. DE still has capacity. Okay, so it looks like the minimum. Okay, so just before I do that, sorry, before we consider the minimum cut, SACBT, that was 2. Okay, so we have 6, 8, that's 10. Okay, is the flow capacity of this network. Okay, all right. So where would the minimum cut go? Okay, so this is something for you to have a think about. Where would the minimum cut go in this diagram? Okay, we need to be considering the edges that are in fact 0. And see this line of zeros here? That seems to be a plausible, I guess, a plausible option. Okay, so if we put a cut through these edges there, okay, and add up the weights of those edges, okay, we have a 1, okay, plus 2, plus 3, plus 4, and that gives us 10 as well. Okay, so there's one way, I guess, just to show how, or the relationship between the minimum cut and the maximum flow by doing both of these methods and thinking, well, where would the minimum cut go if I was to find the minimum cut? If you were asked to find the minimum cut without doing the numerical method, it might be a little bit harder. You can still find it, of course, but this is at least shows the connection between the two. In this video, I'm going to look at another example of the maximum flow minimum cut theorem. So here's an example here that involves 7 vertices. So here's the source, there's the sink, and we'd like to determine the maximum flow of this network. Now, just using cuts alone, there's a lot of cuts that can be made, apart from the obvious sort of cutting off the sink, sort of near the sink, or cutting off the source near the source. There's plenty of other cuts that can be made. So how do I know where the minimum cut should be? Or if I've made a whole lot of cuts, how do I know, or how can I verify which one is in fact the minimum cut? So I'm going to sort of do this in reverse. So I'm going to work out the maximum flow of the network using numerical methods first. And the way I'm going to do that is to look at all the various paths from source to sink, from sort of simplest to the most complicated way to get from source to sink. So the simplest way I can see to get from source to sink is SDT. So using the minimum number of edges that I can find. And SDT, its capacity is 5. Okay, because the 5 here sort of represents the weakest link in the chain, and the chain is only as strong as the weakest link. So if the weakest edge here is 5, or that's the sort of the lowest capacity, well, that determines the capacity of that entire path, SDT. So let's subtract 5 from all that, and we've got 7 there. Okay, another simple way, or a simple path to get from source to sink is SET. And that one is also, has a capacity of 5, so let's put 5 there because SE determines the flow, or the maximum flow of that entire path. So let's subtract 5 from that, and that becomes 9 there. Now, another way to get from S to T would be SDCT. So that's now using 3 edges, SDCT, or 4 vertices. So SD is 7, DC is 10, CT is 4. So the lowest of those edges there is 4. So let's subtract 4 from all of those. So that's 6 there, and that becomes 3. And now looking at this network, there's no other way now to get from S to T. So in fact, if I go SAD, C or SAB, there's no way to get from S to T. So that's it. So 5 plus 5 plus 4
that's 14. So that represents that is in fact the maximum flow of this network, or the flow capacity of this network. So the question is, let's say I made a whole lot of cuts. How do I know which one would be the minimum cut? So the minimum cut would have to cut these three parts somewhere. So if we look at SDT, so this path here, the edge of lowest weight is 5, so that represents the lowest capacity. So I'm going to put a sort of an X marks the spot. Okay, so just there. So the cut or the minimum cut will have to pass this point or cross this point. Now SET, the edge of minimum weight is SE, so the cut would also have to pass through there. And SDCT, the edge here of minimum weight is CT, so I'm going to put a big X there. So that means then that the cut of minimum value, or the minimum cut, would have to pass through these three X's. So it would have to pass through there, and that blue line would then represent the minimum cut. Thanks for watching.